Okay, so we're really happy to have Nima giving us supposedly the last lecture. We'll see.
No, well, yeah, lucky for you guys, I have a cutoff today, so so
Okay.
we will finish today. All right.
Yeah.
All right, great. Okay, so last time we did a crash course on cluster algebras, and I defined the cluster algebras, the associated with the quiver, the notion of a mutation at a node of the quiver, and the mutation rule for the cluster variables. Then we talked about this notion of the G vectors that are a very useful and canonical label that you can associate with any cluster variable, and which have a number of remarkable properties. If we take any collection of cluster variables that occur together in a quiver as we mutate is called a cluster. And if we take the G vectors for all the variables in a given cluster, that gives us a cone in the space in which these G vectors live. And the remarkable fact is that the cones are non-overlapping, and together they tile all of space. And I showed how this is connected in the simple examples where we were talking about the finite type cluster algebras and their corresponding polytopes that give us the amplitudes through to give us up to the one loop amplitudes for the biadjoint bicube theory. That in those cases, the cluster cones, which sort of defines what a cluster is geometrically, these are the kind of smallest cones in this G vector space, are precisely those variables that come together and are interpreted as a single local process in space-time, a single Feynman diagram. And the fact that we have to add them all up together naturally is this other second remarkable fact that they together tile all of space. So both this the fact that there's locality and quantum mechanics, we have to add up all the diagrams as a natural avatar on the side of the structure of these G vector cones. On the other hand, these G vectors are also the normals to the facets of the polytopes that we had talked about. So, if to begin with, you would define the polytopes, for example, by thinking about these positive solutions of the wave equation in kinematic space and their generalizations, then just having that polytope guarantees that all of these G vector cones are just are associated simply with the normal vectors to the faces meeting at a given vertex. And it's a very simple general fact about any polytope that if you look at the collection of the normal vectors meeting at a vertex, that if you plot those normal vectors, you get a cone, and those cones for the different vertices are non-overlapping, and together they tile all of space. So in the simple case of the finite type cluster algebras, this picture of the G vector cones I also explained yesterday that once you have these G vector cones that tile all of space, that immediately tells you that there's a form that's projectively invariant. And if the determinants of all those G vectors in a cone are equal to 1, it also tells you there's a subspace you can pull the form back onto to get the amplitude. So in other words, purely at the level of talking about the form, I can talk about these properties of the form just by telling you about the G vectors. There's one layer sort of up from just the G vectors, which is finding a polytope that has these G vectors as its normal directions. And when you have a polytope that has those G vectors as its normal directions, you can read back down that the G vector cones have all these remarkable properties, that the form exists, that's projective, and so on and so forth. Or you can imagine going up, starting from this collection of G vectors and finding a polytope for which those vectors are the normals. Okay, so in the story of finite type cluster algebras, then we can just think about these interesting properties of the G vector cones. We can think more geometrically, starting from those cones and trying to find a polytope that has that has those G vectors as the normals to its facets. And we can also find a separate origin for that polytope from asking these simple questions of something like the wave equation in kinematic space. So there are sort of two paths to trying to, there are two complementary paths to trying to find these geometric structures. One of them, following your nose and looking at what the G vectors look like, keeping track of how they tile space, and then perhaps trying to uplift them to a polytope. That's one direction. The other is to find a question in kinematic space, a natural sort of dynamical wave equation-like question in kinematic space, to define the polytope ab initio, and then read back down what this pattern of G vectors looks like. In the case of these finite type cluster polytopes for amplitudes up to one loop, both paths are fine, and everything gives you the same answer. But I wanted you to keep both of them in mind because we're going to be using sort of both ways of thinking as we move forward to talk about the most general situation. Okay, so before moving on to talking about the Clusterhedra, I just want to say a few more general things about cluster algebras. One of them I didn't explicitly say before, so let me more explicitly say it now. So let's say you have some quiver. So I'm going to draw. This is just a random one. I don't know why I forgot x3 and x4. Okay. Oh, oops, sorry. 3. Okay. Now, let's say I'm mutating at x2. So I have some formula like x2 prime is equal to, and I would have x5, x7 plus x5, x7, x6. Those are all the outgoing arrows, and incoming arrows I would have x3, x8. Okay, sorry. Okay, so that's my mutation rule. Now, as I mentioned last time, we've been seeing not these nonlinear kind of formulas, but we've been seeing another kind of formula. So if I look at the same quiver, I told you that we can also write down two linear relations. The linear relations are x2 plus x2 prime minus the ones that are connected by going out. So that would be x5, x7, and x6. So minus x5, minus x7, minus x6. That's one linear relation. And another linear relation is x2 plus x2 prime minus the ones that are going in. So minus x3 minus x8. Okay. So we have we either have this single nonlinear relation, or we have this pair of linear relations. And I want to tell you what the relationship is between these two things and where you would get these funny pair of linear relations from. To do that, we have this notion of tropicalization. And it's an extremely simple idea. So we can illustrate it in this example, but let me just say it just slightly more generally. Let's say you have an equation that looks like AB equals CD plus EF. Okay, that's a nice nonlinear equation. But I might be interested in what this equation looks like. So let's say AB, all these variables are positive, let's say. So I might be interested in what it looks like in various extremes. What it looks like as A and B go to infinity or go to 0. So in order to do that, I'm going to put A is equal to e to the little a, B equals e to the little b. Everyone oops, sorry, little e, bad notation. F equals e to the little f. And so now this equation just becomes e to the a plus b is equal to e to the c plus d plus e to the e plus f. Okay. And in fact, let me now imagine putting a parameter here that I'm going to control to sort of send things to infinity. So maybe I'll put a t here in front of everyone. Okay, so I have an e to the t in front of all of this. Okay, and so now imagine what happens as t goes to infinity. And as t goes to infinity, this equation simplifies. Oops, sorry. So let me just write it again. This equation, e to the t a plus b equals e to the t c plus d plus e to the t e plus f. That equation simplifies, and what I get is that a plus b is equal to, well, it just depends who is bigger, c plus d or e plus f. Okay, so whichever is bigger, a plus b is equal to the max of c plus d and e plus f. Okay, so you see, I started with an equation ab equals cd plus ef. This is a nonlinear equation, but from this nonlinear equation, I get this almost linear equation. Okay, I get this almost linear equation. A plus b is, you see, a plus b is either equal to c plus d, so in a whole region of a, b, c, d space, a plus b equals c plus d, but then there's a wall. And when c plus d becomes smaller than e plus f, the equation switches to a plus b equals e plus f. So this is called piecewise linear. Okay? So instead of staring at this nonlinear equation, this quasi-piecewise linear equation captures a lot of the same nonlinear properties of this equation. So this top equation is known as the tropicalized form of the bottom one, and the tropicalization is the rules are very simple. We've just seen them here. That if I have a times b, the tropicalization of that is a plus b. And if I have c plus d in general, the tropicalization is to put a max here, a max of c and d. And in this way, you can take any expression in terms of the capital A, B, C, Ds or anything and find the tropicalized version of them. So in particular, when I look at the tropicalized version of the mutation relation, the tropicalized version of this xx prime equals xxx plus xx is the max of is the tropicalized form would put a max there. Okay? And therefore, it tells you that that there are some regions in this X space. You can call them tropical chambers. There's some region in X space where you have to just choose which one of these two is actually max. Okay, so that's what I mentioned. What I mentioned last time is that if I take the set of all the mutations, with each one of them, I get this pair of linear relations, but then I have to decide to keep one of them. But keeping one of them is like choosing some tropical chamber, some choice of which one of these guys is going to be max. And there are some consistent choices that, after all, in the whole space, some of them are max. Okay, so that tells you that that chamber, one chamber at a time, I get to choose one of these two linear equations. And that's the tropicalization of the whole cluster algebra. Now, a remarkable fact is that the tropical chambers are actually in bijection with a choice of cluster. So if you choose some initial cluster, making a choice of initial cluster is actually in bijection with choosing a tropical chamber. And having made a choice for an initial cluster, there's a set of these choices for who is max. So in other words, there's a way of choosing one of these two relations for every mutation, which are all consistent with each other. Okay? And such a choice then gives you, if I set all of these things equal to 0, I can think of using that to determine, those are linear equations that determine all the rest of these x's for the other cluster variables in terms of the ones in some initial cluster. And that expression that expands the x's in terms of the initial cluster are the g vectors. Okay? So there was something funny that appearing that the choice of g vectors, what you get for the g vectors depends on the choice of initial cluster. But that is reflecting the fact that there are lots and lots of different tropical chambers. In every tropical chamber, there's one of these expressions is max. So one of these terms is dominating. But in each one, this set of linear equations lets you determine all the g vectors. So equivalently, all the g vectors satisfy all of these linearized mutation relations, but again, only one of the two, and only one of the two set are consistent chamber by chamber. Okay, so that was just something that and again, everything that we've seen in our previous discussion involved these linear equations. Okay, but it involved both these linear equations and a choice of cluster. Even if I go back to if I phrase that we saw earlier on, I remember when we were talking about this kinematic space when we're talking about this kinematic space for the icosahedron, I said that you could draw all kinds of let me see if I have it up here. Yeah, we could draw all kinds of chunks out of the space-time, and you see, making a choice for which chunk you take out of the space-time is actually making a choice of initial cluster. In this case, the initial cluster is just given by what this past surface is. So our rule here, remember, was that we drew a quiver that looked like this, let's say, associated with this 1, 3, 1, 4, 1, 5, 1, 6. Whereas here we'd have a different initial. Here we'd have a different initial quiver. Here we'd have 2, 4, 1, 4, 1, 5, 1, 6. So the arrow would be reversed here. And depending on what your initial surface looks like, your expression for what the x's inside look like in terms of the initial ones will be different. Okay, so the sort of choice of initial cluster is like the choice of initial Cauchy surface in this kinematic spacetime. And so the expression you get inside, of course, depends on where you put the initial condition. So the expression for solving for this x36 inside here, using this wave equation in terms of the initial 1, 3, 1, 4, 1, 5, 1, 6. If I expand that x36 in terms of the initial guys, that would be the g vector for x36. But that expression would obviously be different than the expression that I get doing the expansion in this. Okay, so
sorry, Nima.
Yes.
So if you had a initial cluster that's not acyclic, you still have a tropical chamber. Everything is still fine.
Yes.
But you won't be able to do the walk, and you won't be able to draw it on the kinematic spacetime.
Yeah,
right?
That's right. No, so that statement is even more general. I'm just saying that in this previous picture we saw that the expression you get for the guys inside depends on it depends on the choice of the initial surface. There are some choices of cluster that we can't even represent in the simple way in the kinematic space. Indeed.
Right.
Okay. So let me go back now. Okay. So that was. All right. Okay. So let me now switch to telling you one last bit of useful information about cluster algebra, specifically for surface cluster algebras. So I want to give you a simple picture for computing the g vectors of surface cluster algebras. And I'm not going to prove any of this, although I think as we go, you'll get a good sense for how the proof works. So what do I want to do here? What I want to do is, let's even say for AN. So let's say I had so we know that that a G vector depends on a choice of initial cluster. Okay, so so here an initial cluster is some triangulation of this hexagon. Let me choose some triangulation of the hexagon. Let me just for fun choose this one. Okay, but now what I would like to know is, without staring and doing any algebra, without doing any drawing quivers, doing mutations, anything like that, I just would like to know, if you give me any old variable like 2, 5, 2, 4, let's say. So here's any other variable. Let's say 2, 5. I just want to be able to write down the G vector for 2, 5 with in some transparent way. I mean, this is all the data there is, right? I just have this triangulation, and then there should be a formula for the G vector of 2, 5 that will be expressed as some linear combination of 1, 3, 1, 4, and 1, 5 in this picture. Okay? So that's what I would like to. That's what I'd like to explain. All right, and so here's the rule. It's extremely simple, and already I'll illustrate it in this example, but then we'll talk about it in slightly more interesting examples in a second. So let's say I want the G vector for 2, 5. What I'm going to do is I'm just going to draw that arc 2, 5, except instead of drawing an arc, I'm going to do what's called a lamination. Never mind what this means. Never mind the choice of word. What it means is that when my arcs touch the boundaries, I'm not going to have them touch the boundary point. Instead, I'm going to just rotate them slightly away from the boundary point, but I'm going to rotate them in the direction that's sort of given by the orientation of the surface. So here I've always oriented my surfaces to be clockwise. That means that instead of drawing 2, 5 like that, I'm going to push the 2 slightly to the right here, and that's what I get from the orientation here, and the 5 slightly to the right here as well. Okay, so I'm now going to draw the following. So I'm going to draw the following arc. Instead, the one that I want is 2, 5. I'm just going to slightly rotate 2 and 5 in the way that I described. Okay, so so now I have this guy. So erase 2, 5 now. Okay. Okay, and now I want I want a formula for a G vector, which is G is equal to something times x13 plus something times x14 plus something times x15, right? I want to figure out what those numbers are. And the idea, and now I'm going to give you a rule for figuring out what the coefficients are. So for every arc in the triangulation, I'm going to assign an integer. Okay? And that integer is going to be the corresponding coefficient of the G vector. Okay, so what is the rule? Well, the point is that every arc in the triangulation is part of a every arc in the triangulation is sorry, not part of a, let me just say this properly, is the diagonal of a unique quadrilateral. Okay, after all, and what happens, a mutation is just taking that unique quadrilateral and taking our arc, which is a diagonal, and replacing it for the other diagonal. Okay, so for example, here 1, 3, 1, 3, 1, 3 is the it uniquely belongs to this quadrilateral. Okay, and if I wanted to mutate 1, 3, I would replace it with replace it with 2, 4. Okay, so every arc is so I can think of every arc in the triangulation as belonging to a quadrilateral. Okay, and therefore all we do is we stare at that quadrilateral, and so let's say it doesn't matter how I've drawn it. Let's every line. So I draw my shifted arc. So my lamination, I draw my shifted arc, and then I just look to see. So I'm interested in the coefficient of this arc in the triangulation. I just look to see what my curve, what my lamination does as it crosses through this quadrilateral. If it crosses through the quadrilateral like this, and here the mnemonic is that if it crosses like this, then it crosses it in the pattern of a Z. So it looks like a Z. So if I look at the edges that it crosses, it's making a Z. If it's the Z pattern, I write down a -1. Alternately, if it crosses like this, so let's say again, it looks like that. If it crosses like this, so this you can call the S pattern, because again, if you look at the edges that this lamination crosses, okay, then if you tilt your head by 90 degrees and just imagine drawing the line vertically, so the green line vertically, then this is the S pattern, and you get a +1. Okay, and otherwise 0. Okay, so for instance, maybe it does something like this. Maybe this is your quadrilateral. Maybe the lamination doesn't cross it at all. Fine, but it could cross it. But if it doesn't cross on opposite sides, then you just get 0. So if I had something like that, it would be 0. Okay, and as we'll see, in general, for interesting laminations, you can have lots of crossings. So I can have something that looks like this in principle. If I have something that looks like this, say, then I would get from this -2, because it's the Z pattern. It crosses like a Z, but there are 2 lines that are crossing, so I get a -1 for each one of them, and so I get a -2 in total. Meanwhile, these ones here don't contribute at all. Okay? They don't cross or contribute at all. Okay, so in this way, we can just immediately read off the G vector. All we have to do is stare at the triangulation, draw these quadrilaterals, and we're done. So let's just do that. Let's just do a few of those examples. So if we do this guy, so if this is my triangulation again. So let's read off the G vector for 2, 5. Oops, I drew it in blue. Okay, then let us look at 1, 3. Okay, so if I look at 1, 3, this is crossing 1, 3 in the Z pattern. So this is a negative x13. Okay, so you see then it's also crossing 1, 4. So but how is it crossing 1, 4? Well, you see, if I look at this quadrilateral, if I look at the 1, 4 quadrilateral there, then it's going in one side, but it's not crossing the opposite side at all. So it gets no contribution at all from 1, 4. And finally, let's look at 1, 5. So here's the 1, 5 quadrilateral. And now for 1, 5, you see it's the S pattern. Okay, so it looks like it's crossing it in an S pattern, so I get +1, 5. Okay. All right. So that's a very useful way of getting that's a very useful way of getting the G vectors. And you can convince yourself that sort of 80% of the proof of why this is correct is just see what happens. You can see what happens after you can see that these rules are compatible with the x plus x minus x minus x relations that you expect from mutation. I won't say more about that, but it should be pretty intuitive that since we're just keeping track of how these laminations cross through the quadrilaterals, that when we do a mutation, that the G vectors satisfy those x plus x minus x relations as they should. Okay. Okay. So all right. So let's now actually do another example, because we're going to talk about this example more in a moment. Let's look at what we can call A1, comma 1. Okay, so this is a surface with just one point on the boundary. So we talked about this briefly last time. 1, 2. Okay, and I'm going to label these guys. Let me label this. I'm going to label this arc A0, and this one that winds around the other way, I'll label A minus 1. So the first thing that we should do is draw the triangulation. So we talked about how to do this. We talked about how to do this without thinking last time. I'll just write it again. So let me just label these loops alpha and beta. And then we have, oops. So there's 1 and 2. Okay, and so here was our triangulation. So this is 1, 1, beta, 2, 2, alpha, and here's A minus 1 and A0 and A minus 1 again here. So the A minus 1s are identified, and since we're going to want to think about all these quadrilaterals where every variable is a diagonal of a quadrilateral, so A0 is manifestly the diagonal of a quadrilateral. A minus 1 is not, but we have this identification. So let me just extend the picture. So again, I'm just doing a copy of this triangle, this upper triangle. I'm just drawing it down here again. So this is the point 2 again, that's alpha, this is A0. So these things are identified, but now conveniently, both A0 is the diagonal of this quadrilateral that I just see, and A minus 1 is the diagonal of the second quadrilateral down here that I can just see. Okay, so all right. So this is my so this is the surface, and this is we have the surface and we have the triangulation. So we can now proceed to looking at the G vectors. So let's look at some. So for example, just one quick sanity check. Let us look at the G vector just for A0. If I look at the G vector just for A0, I should just find A0, right? So what should we do? So remember, we have to shift the points in the direction given by the orientation of the surface. So that means that up here, to draw my lamination. So I want to draw A0. So I want something to go from 1 to 2, but I'm going to shift slightly clockwise from 1 and counterclockwise for 2. Okay? And again, those directions are just dictated by the orientation of the surface. So because the surface is oriented like this, up at the upper boundary, it's pushing the points to the right. At this inside boundary, it's pushing the points to the left. So, all right. So, all right. Okay, and so now let's look at the let's draw the arc. So there's an arc. Okay, and so let's see what this looks like on the on our triangulation. So here we're starting from beta. We're starting from beta. We cross through a minus 1, and then we cross through a 0. So here I'm crossing through a minus 1, then I'm crossing through a 0. Now remember, this bottom triangle is the same as this top triangle, so I'm just going to keep drawing it. I'm going to draw the image up there. So we cross through a minus 1, we cross through a 0, then we cross through a minus 1 again, and then we end at alpha. So I'm going to do that. I'm going to cross through a minus 1 again, and I'm going to end at alpha. Okay, so that is what our lamination looks like on this surface. And now let's look and see A0. The A0 quadrilateral is up here. And indeed, we see that this line crosses through it like an S. I get a plus A0. But A minus 1 quadrilateral is down here. And you see nothing is passing through the opposing side. So I just get plus 0. All right? So we see that our rules indeed work. They're consistent. The G vector for A0 is just A0. Okay? All right. But now let me do the next most interesting example. Okay, so so now I'm going to look at, so here I have something that is, I have something that was, I have something that is winding around in this direction, a minus 1. So I'm going to look at the variable that's winding around in the opposite direction. So I would want to have the guy that's doing this. Okay, except I have to draw it as a lamination again. Okay, so let's just do that. So if I'm going to draw it as a lamination, I'm going to put 1 point here, 1 point there, and then draw it like that. Okay. Okay, so let's look at this curve in the picture. Again, I'm starting from beta. I first pass through a minus 1 and then a 0. So that's the same as we saw before, a minus 1 to a 0. So it comes back out here. Then I'm going to, after I cross a 0, I'm going to cross a minus 1 again. Okay, so here I'm crossing a minus 1 again. After I cross a minus 1, I'm going to cross a 0 again. So here I go. I have to keep crossing a 0 again. And again, this segment up here is the same as here. And after I cross a 0 again, sorry, I'm going around here. So I cross a minus 1, then a 0, then a minus 1, and then I have to cross a minus 1 again, and then I hit alpha. All right, so I'm just drawing this curve on my triangulation. Okay, and now this formula is a little more interesting. If I look at the A0 quadrilateral up here, you see I have two things going through it. So from here, I get 2A0. But now if I look at the A minus 1 quadrilateral, I do have this curve going through it. This curve goes through it, and it goes through it in the Z pattern. So I get 2A0 minus a minus 1. Okay, so that's a slightly more interesting G vector. Okay. Now, let me keep going again. I want to go back to this picture. And now I want to have something like a minus 1, but which winds one more in the a minus 1 direction. Okay, so I want to have, oops. This guy. Okay. So let's look at this again. So we start with beta. We pass through. Now we pass first through A0, then we pass through a minus. Sorry, this is even simpler. Apologize. here we just pass through A0, and that's it. We pass through A0, and then we just keep on going. We just keep on going to alpha. So it just looks like this. Okay, so this just intersects A0, and it does so in the Z shape. So what I get from here is negative A0. Okay, well, let me just start recording some of these guys. So I just did 3 examples. So hopefully you see how simple it is and how it goes. But now I want to record these G vectors in this plane of A-1 and A0. Okay, so to begin with, I had my initial cluster, which looks like just the basis vectors here. Okay, this next one that we computed, this first non-trivial one, it sort of winds. So if this first one is A-1 and then A0, then this blue one is winding 1 in the opposite way, so that deserves to be called A1. Okay, so let's just call that A1. So we saw that the vector for A1 looks like this. It was 2A0 minus A-1. So this vector is minus 1 comma 2. Okay, so this is 0 comma 1, 1 comma 0. Then the guy that the second one that we did, the last one that we did, this one is sort of winding in the same direction as the A-1, except 1 more. So if we're going to call this red one A-1, then it's sensible to call the blue one A-2. So we see that A-2 is given by this. And I'll just tell you what the rest of the answers look like. So you'll find, so this is A1, A plus 1. You'll find that A plus 2 is minus 2, 3. And they just keep on going. They get longer and longer in this direction. And also on this side, so A minus 2 is 0 minus 1. A minus 3 would be minus 1, 0. And then similarly, they would just start getting longer. So in this direction, I'd have A minus 4, and this one would be minus 1, minus 2 comma 1. And then the next one, A minus 5, would be minus 3 comma 2. And they would get longer and longer, but they would asymptote to this direction. Okay, so there's this direction where the unit vector, I mean the first integer point along that direction is minus 1, 1. Okay. So that's what all the G vectors look like in this example. And now let's look to see who the various who the clusters are. Well, even the ones that we just computed, but we just begin with the initial cluster. So so this set, so A0 and A1 is in the initial cluster, and again nicely. So this is a cone in the problem. Okay, this is those 2 G vectors span a cone. Now let's look at the next one that we computed. So this guy, if I now draw again who it is. Now if I draw the actual arc that it was to begin with. So here is A0, here is A1, A minus 1, and we're drawing A1, which is that guy, right? So notice that if I mutate it at A minus 1, so if I began with A0 and A minus 1, if I mutate at A minus 1, that means that I should remove a minus 1 and add an arc that I'm now allowed to add that I wasn't allowed to add before, right? That's the whole point, that the triangulations are maximal set of compatible arcs. So to find what somebody mutates to, you just delete that arc, and then you see who can I now draw instead of the one that I added, and there should always be a unique person that you can draw instead. So the unique guy that can draw instead is exactly that one. It's exactly A1. Okay, so in other words, if I look at my my clusters, I began with A0 and A1, and in fact, if we drew the quiver, it would look like this: A0 and A minus 1, and after we mutate at A minus 1, we have this guy. We have A0 and A1. Okay, so I just mutated at A minus 1 to give me A1. All right, so if I go back to this picture, that's this next one over. This next one over is A0 and A1, and so we have this cone. So again, we're seeing the sort of general pattern that I told you, that the G vectors for any cluster are non-overlapping cones, and together they are tiling space. Similarly, if we look at the other one that we computed, is exactly this guy down here, and so on. Okay, so we can take all of them, and the pattern continues in the same way. Okay? But you notice that in this example, there's something interesting, which is that while the cones they're non-overlapping, there's no holes in this space. They don't quite cover the entire space. They're missing this direction minus 1, 1. Okay, this direction minus 1, 1 is not officially covered at any point. The G vectors asymptote to that direction, but they don't ever get there, and also the cones don't cover it. Okay, so that's the first novelty that we see beyond the case of finite cluster algebras. Okay, now this direction minus 1, 1 has a very beautiful interpretation, and also the fact that these cones are so notice that these variables here are that the variables on the top are sort of winding more and more in the positive direction. So they're sort of positive winding. The ones down here are winding more and more in the negative direction. And if you just look at what I've drawn, you can see that on the positive winding side, a positive W plus 1, so let me just call it a plus, just to remind me that it's positive. A positive winding plus 1 is just equal to a positive plus this vector minus 1, 1. And on the negative side, a minus negative winding, negative 1, again, more negatively wound, is a minus negative W, again, plus exactly the same vector, minus 1, 1. Okay? So we can just sort of observe that from this picture. Like I go from 0, 1 to minus 1, 2 by adding minus 1, 1. And then from minus 1, 2 to minus 2, 3 by adding minus 1, 1. Okay? So that explains why the G vectors asymptote to this direction, minus 1, 1. As we go asymptotically, we just keep adding minus 1, 1. And they all asymptote to this direction, minus 1, 1, both from the positive winding side and from the negative winding side. So the first thing I want to do is explain something about what this direction minus 1, 1 is, and its natural geometric interpretation. To do that, let's come back to our picture. And let's draw another obvious variable. Now, this variable never shows up in a triangulation. Okay? This variable obviously never shows up in a triangulation, but it's also obviously a very natural variable in the problem. This one, this loop that surrounds the annulus. Okay? So I'm going to call this variable delta. Okay, so it's this interesting loop, and let's compute its G vector. Okay, so this notion of calculating G vectors, I can, if you give me, well, first for any old cluster algebra, I gave you a definition last time of G vector purely in the following way. If you give me any sum of monomials in terms of initial cluster variables, then each monomial gives me a certain exponent vector, and the G vector is one of those exponent vectors, and the one that's smallest in the sense that all the other ones can be, all the other exponent vectors can be expressed in terms of the smallest one by adding the rows of the B matrix. So by taking positive linear combinations of the rows of the B matrix. So that is a way of getting a G vector for any variable, not necessarily a cluster variable. And also, and that's true for any old cluster algebra, but specifically for the surfaces, nothing stops me from just following exactly the same rules that I just used for defining G vectors to figure out what the G vector is for these loops. So let's see what I would assign as a G vector for this loop. So what is it? It's something that, let's say it starts at a minus 1, it intersects a0, and then to a minus 1 again. So it just whoop, goes through the whole space like that. And now let's look at what its its G vector again. It crosses through the a0 like an S, and it crosses through this a minus 1 quadrilateral like a Z. So delta is equal to exactly a0 minus a1. And so its corresponding G vector is exactly 1 minus 1. Okay, so this is exactly the vector that we just saw. Okay. Oops, where did my picture go? Sorry, written in this is the vector minus 1, 1 because I chose, because I put a minus 1 on the x-axis. So oops, where did it go? Okay, sorry. Delta is a0 minus a1, and it's this vector minus 1. All right. So we see that this. So we see something interesting here. First, we have this basic fact that we can sort of generate all of the G vectors for the positive winding and the negative winding sector separately, just by shifting with delta. Okay, so and then that tells us that all the G vectors asymptote to delta as I wind around more and more in the positive and the negative direction, and therefore this picture of the G vector tones piles, but asymptotes in exactly the way that we talked about before. Okay, so I can rewrite this just as this plus. So this is the G vector for delta, and I can write these formulas saying that I'm shifting by delta. Now, let me give you yet another way of understanding why this is true. So let's go back and look at, let's draw this picture. Okay, so let's say I draw this variable a0, here's a0, and here's delta. And now, at the level of the whole cluster algebra, not the G vectors, I know that there's going to be a formula that looks like a0 times delta. So remember that any curves that cross, I'm supposed to be able to compute. Well, there's a relation, which is the Skene relation on the surface. So a0 times delta would equal. So what am I supposed to do? I'm supposed to take these. I'm supposed to take these two things that cross and uncross them one way. I could uncross this like this. So if I uncross it like this, what do I get? Well, that's exactly what I called A1. Or I could go back and uncross it the other way. So like this. It was like that. I can uncross it the other way. and that's plus a negative 1. Okay, so this is also just a formula for delta as a cluster variable. But now you see it's clear that this formula will be true no matter how much I wind the loops, because delta is obviously is invariant, obviously rotationally invariant. So I would get exactly the same formula if I took A for any winding times delta, positive or negative, is equal to the A winding minus 1 plus the A winding plus 1. Okay? Oh, that's at the level of the full cluster algebra. Now, what does the tropicalized version of this formula look like? The tropicalized version is just telling us so tropically, remember the story about G vectors is about the tropical version. It's just telling me that A winding plus delta is either equal to A winding plus 1 or A winding minus 1. Okay? And so that's what we're seeing here. What we're seeing is that we have this surface, if you like, we have the surface. We have a symmetry of the surface, which is just the action of the mapping class group. It's a fancy way of saying it, but here it's just obviously where I can take the, let's say, inside annulus and just rotate it. Okay, that doesn't change the surface at all, but it changes these arcs. Right? And of course, it changes the arcs. It gives me. So if I do that, if I start with the arc A0 and I just rotated the inner annulus, I'd get the other arcs, either winding in one direction or winding in the other. And the really interesting thing is that the action of the mapping class group on the G vectors is almost linear. Okay, it's almost linear, and here we see it. Here we see that on the positive winding guys, it's just linear. It just shifts with delta. And on the negative winding wise, it's also linear, but it's a different linear transformation. Okay, so there isn't one uniform linear transformation. I'm not saying that all the AW plus 1s are just given by AW plus delta, but there's one sort of chamber, the negative winding side, where the action of where it acts linearly just by the more and more negatively wound guys get shifted by delta, and separately on the positive. So this feature, again, this is the interesting part of this of this whole way of thinking about the G vectors and the cluster algebra. Cluster algebra is a very naively very nonlinear beast, but working in terms of the G vectors linearizes what's going on as much as possible. And so we see that the action of the mapping class group is acting quasi-linearly. It acts on the positive winding sector and the negative winding sector separately. So again, we see it in this picture. It's not true that I take this vector here and I just keep adding delta to like go all the way and bring it out there. Not at all. I have my initial cluster. I have my initial cluster here, and then I have the adjacent clusters like this one and that one. So I have to sort of move backwards some amount. But then after I've done that, now from I just move back one step, but from this step forward, I'm shifting with delta, and from this step forward, I'm also shifting with delta. But over right in here at this sort of juncture, there's no, then I don't get from this variable to that one just by shifting with delta. Okay. All right. So let me pause there and see if there are any questions.
Sorry if I missed this, but is there a interpretation for the length of the G vector?
No. There's no metric on this space at all. There's no metric on the space, but there is something important. I'll make this interesting point. There is something important about the determinants of the G vectors that you see in a cluster. So that this kind of volume of that cone made from the G vectors it's a very interesting fact for the well, it's a kind of pretty simple fact that the G vectors for that those determinants for cluster cones are all plus or minus 1. Okay, and the sort of simple reason to see why it has to be true is you start with the initial set, which is just the basis, the usual basis. So there is obviously 1. But then when you do a mutation, you always have a formula like x prime plus x is equal to a sum of the other x's. So that means that x prime is negative x plus the sum of some other x's. And so that means that the new vector that you're getting is just reflecting through it's just taking that cone that you had and just reflecting one of the vectors through a facet of a number of the others. And so the new determinant is just opposite in sign to the old one. So since you start with 1, the new one that you get will be minus 1, and the one that you get after that will be 1, and so on. So the magnitude of all the determinants of the cones are 1. You see that in this example too, right? In this example, even though the vectors are getting longer and longer, every one of these areas is 1. Okay? Every one of those determinants is still 1. Okay?
Yeah, I get it. One more question is, so here there is, there is only one vector that is sort of missed out in this space, in this entire space. But now suppose if you had two sort of, like two holes, then you would have multiple possible deltas.
Yes,
and that is why you get
deltas. And in fact, what the story, I'll tell you something about what happens I'll tell you something about what happens in general towards the end of the talk.
Okay.
But absolutely, we have multiple deltas, and it can actually get even more interesting than that. You can have deltas which have their own complicated windings around each other, and so on. Okay, so beginning at 3 loops and above, and actually even at even 2-loop non-planar, we get infinitely many deltas as well. Okay, so but we're not there yet. We're just talking about the sort of the simplest example first.
Okay.
Okay, is there another question? Yeah. So the question is, when you tropicalize, how do you get B or C on the right-hand side instead? No, it's not. I mean, it's just that in the whole giant in the whole cluster algebra, we actually have the actual mutation relation, and that means that anywhere you are, when you tropicalize, one or the other of the expressions will be max. Okay, so so that means that there's some whole region, a continuous region of the G vector space. There's a whole continuous region of space where one is dominating over the other. In that region, you have a bunch of every mutation has just one of the two. You choose one of the two. Now, it's a quite nice fact that if you forgot about all the stuff with tropicalization, just totally forget about that. Instead, you say, look, for every one of these mutations, I want to write down some formula like x plus x minus the sum of the arrows in or the sum of the arrows out. But there's no reason a priori to choose one over the other. So, but let me just make randomly a choice. For this mutation, I choose minus. For this mutation, I choose incoming. For the other one, I choose outgoing. You make some random collection. In general, you have vastly more equations than unknowns. Okay, and so those equations will just be garbage. They won't be mutually consistent. There's only a particular combination of ways that you can choose one of the two equations for each that are actually mutually consistent. All the ones that are mutually consistent, you can actually think of as having as being one of these sort of tropical chambers of tropicalizing the underlying nonlinear mutation relations. But once you tropicalize the underlying nonlinear mutation relations, then all of this sort of X space gets broken up into chambers where consistently one of the two relations is max. Okay, so you don't have now, and it's a separate non-trivial fact that set of chambers is actually in bijection with a choice of initial cluster. Okay, so if you look at if you just look at the consistent a consistent choice for which one of the two terms you choose, that choice allows you to express all of the x's in terms of some particular basis, and the choice that you get are the g vectors, the same as the g vectors that you would get by choosing that set as your initial seed and expanding everything else. Okay. Okay. Any other questions? Okay. So all right. So here we just we went through this example just to illustrate some novel points, but also just to show how easy it is to determine g vectors from triangulations of surfaces in this way. Okay, so now I want to move on to talking about Clusterhedra, unless there are just one more second to see if there are any questions. Okay. Okay. So so let's now start talking about Clusterhedra. Actually, all right. So now let's start talking about Clusterhedra, and let's recall again what it is that we're trying to do. Let me see if I find the slides. In general, we're interested in these H-trace. We're interested in H-trace Feynman diagrams of genus G with L loops. Remember, if we're talking about the biadjoint phi cube theory, there's really two sets of colors. So in this entire discussion where we're just summing these Feynman diagrams, we're imagining summing the Feynman diagrams on surfaces, L loops drawn on surface of genus G. Any trace factor that we have is associated with a boundary component inside this Riemann surface. If there are M traces, if there are M generators in the trace, there are M marked points on the boundary. And also, if we're summing, for the biadjoint theory, we have two colors. So we're imagining that the ordering for the traces in the one color factor is exactly the same as in the other color factor. If we do that, we're summing over all the planar diagrams, all the diagrams that we draw on these surfaces, sorry. Now, if the ordering of the two sides were different, then we'd only keep the subset of the diagrams that are compatible with both orderings. So, but all the diagrams there are, we don't get any new diagrams. It's just the same diagrams, we delete some of them. So if we want to look at the, we're just talking about the amplitude, which is the one where the traces are the same on both sides. And so the sort of combinatorics and the diagrammatics is exactly the same as a normal large N theory with just one color. And as we discussed, in general, these are, we're always drawing the jewels of these diagrams. And it's a sort of simple fact that the jewel of a diagram drawn with L loops on a surface with the genus G.
I think the screen is not being shared.
Oh, I'm sorry.
Yeah, screen is.
Right.
Sorry. I thought I was sharing already. Thank you. Oops. Sorry, that's not it. There we go. Yeah. So it's a simple fact that the dual of such a diagram is a triangulation of the surface with same genus, the same number of boundaries, but a specific number of punctures that's related to the number of loops and the rest of the data by this simple formula. So in general, then, we're going to be thinking about triangulations of surfaces of general genus with a general number of boundaries and some number of punctures. Okay, and so that's what we're interested in thinking about. But what's the challenge? So the novelty is the following. And we've seen it already in our previous example, but let's see it in a slightly more familiar example. If we're talking, let's say, about two loops, still just planar diagrams. So then we draw. Now we have two loops, so we have two punctures on the inside. And what the problem is that while this loop variable. So I could complete this triangulation in many ways. Let me just, so there are lots of ways I can complete it to triangulation like this. Anyway, I do something on the outside here. So there's a triangulation, okay? That triangulation is dual to some Feynman diagram. In that Feynman diagram, this arc would correspond to some part of some loop variable. That would be some loop variable, and so on. This would be the loop variable between, like in a double box. It would be an internal loop variable, and so on. Okay, that's perfectly fine. But now let me take this surface, and now there's an action of there's an action of the mapping class group on this surface where I just take those two punctures and I rotate them. If I rotate them, I'm not changing anything about the surface. The dual diagram is exactly the same Feynman diagram. I'm not changing, so from the perspective of the dual, nothing has changed, but obviously the variables have changed, okay? And the triangulation is different. It's related to the original triangulation by this rotation, but it's different, okay? And so or said another way, we have infinitely many variables that label what we would like to think of as the same loop variable, okay? So if I go back to just drawing this guy, then I can have this loop, but it can also wind around the other puncture once, wind around the other puncture twice, wind around it any number of times. Okay, so that is the novelty that we have to deal with, is there's infinitely many variables, and so we're in the infinite type cluster algebra. And in this case, by the way, you also get a simple understanding for why it is that we get the same quivers back over and over again, but infinitely many variables. But the quivers are just dually capturing the actual Feynman diagrams, okay? So, and that's why we get a finite number of quivers for these triangulations of surfaces, because there's a finite number of triangulations up to this dumb rotation of the mapping class group, okay? So that's why there's a finite number of quivers for these cluster algebras, but infinitely many variables. And the infinite is just coming from this action of the mapping class group. Now, if I'm just talking about planar diagrams, so just a disk with endpoints on the outside, but L punctures, then the mapping class group in that case is just a braid group. Okay, so that makes sense. You have L punctures, and I can just swap them around, braid them any way I like, and I don't change the surface. Okay, so the mapping class group is a very interesting non-abelian group when L is large, when L is 3 or larger. When L equals 2, it's just the sort of U1. For L equals 2, it's just the winding around one way, winding around the other. Okay. Now, as I've said a few times, also, the G-vector cones still fit snugly together, but they leave lower codimension holes in the space. So we saw that in our previous example, that everything asymptoted in the direction delta, and so there was something that was missing that was not covered by the G-vector cones, but is lower codimension. Just in that case, the space is two-dimensional, but there's just sort of one ray that was missing. Now, this is a beautiful fact for all surface cluster algebras. Totally generic cluster algebras are worse than this. They have honest top-dimensional holes missing that are not covered by the G-vectors, but the surface cluster algebras are dense. The G-vector cones are dense, but they can miss lower codimension spaces. Okay, so, but already the fact, saying nothing else, this is the 0th order point I wanted to make. Saying nothing else, if you ignore everything else I say in the rest of the discussion of Clusterhedra, already we know how to assign signs to every diagram so the whole form is projectively invariant. And it's just given by the sign of the determinant of the G-vector cones associated with every cluster. And that, again, reflects, so there's already this deep fact that the cones that the cones are non-overlapping in tile, and that already tells us that the form is guaranteed to be projectively invariant. But you see, if I stop at any point, the cancellation is telescopic. So as we saw in our first example of how the projectivity works, what's going on is that when I do the projective variation of the form, I have to take so when I do this, let me just open this. When I do this projective variation of the form, let's say all these xij's goes to alpha of x times xij, then under the projective variation of the form, I get something like d log alpha multiplied by something which had a partial triangulation where I lost one of the variables and everything else was already factorized, but I had a sort of 4-point in the inside. Okay, so that meant that the coefficient of all of these guys had to vanish. So what is that? In the language of the G vectors, this is just like, this is just like saying that there's a variation where I have a cone over here, and I have another cone where I flip one of the variables sort of over here, but the rest of where I just flip one of the variables through the plane made by the other two. And so I'm drawing it badly here. But essentially, for every codimension 1 face of the cone, you have something that needs to vanish. Okay, so for every codimension 1 face of the cone is precisely a collection of n-1 cluster variables that are all compatible with each other. And there are 2 that I can use to complete it with a triangulation. So I have one set over here and one guy, which can complete it to a full triangulation or full cluster. And then I can mutate this to the other side. But that means that in this projective variation, there's d log alpha multiplied precisely by the d log of all the x's on this sort of on this facet of the cone. So that means for every one of these collections of x's, there's a check that has there's a check for the projective variation to cancel, and every one of those checks is passed because the cones all fit together snugly. The only problem is that there are some cones at the end. There's infinitely many of them. So it's a sort of a telescopic cancellation. And there's a cone at the end which is not canceling. Formally, if you let the sum go over everything, then you could maybe ignore the one that happens at infinity. But anyway, that's a little bit funny, and that we're not going to be doing that. But I want to stress that already most of the projectivity is checked and is already a very non-trivial fact, which is reflecting this snug fitting together of all these G-vector cones. Essentially, the rest of our story is to figure out how to compactify this whole infinite space to something finite, and then the whole thing will be projective. And anyway, then things will be more canonical and nicer after we do that. But I did want to stress already that the projectivity is mostly given to us for free. This very non-trivial projectivity of the form is mostly given to us for free just by this, just by basic facts about G-vector cones. Okay, so anyway, that is our that's our challenge. We somehow want to compactify this infinite space to get something finite. Okay, so that's what we're looking for. So we're going to call these clusterhedra. And what the sort of properties we would want for such polytopes are, first of all, we'd like to be able to unambiguously associate the vertices with diagrams or clusters. Okay, so that was the point, is that some polytope whose vertices are clusters. Now we have infinitely many cluster variables, infinitely many clusters. It's not obvious there is any polytope, so that's part of the issue. So we want to have something that somehow compactifies it. It's finite. But vertices we can all associate somehow with diagrams or clusters. Furthermore, we would like that the G vectors that we've seen, as we saw in finite type, are among the facets. Okay, so the sort of picture you want to have in mind, and we'll see a concrete example in a second, is that we have this polytope which would naively be built up and have infinitely many sides. So we want to stop it somewhere. We're going to stop it somewhere and sort of cap it off with something else. And we'll see this explicitly in a second. But what we'd like is that every vertex that we see, the cap isn't some random crappy thing. Every vertex should have a meaning should look like, should be associated with with diagrams or clusters in a canonical way, and that all the G vectors that we saw will be the finite number of G vectors we see will actually be normal facets of this polytope. We'll maybe see some other faces. We'll talk about what the other faces are. Of course, the canonical form for this thing will be projective. That part is trivial. But the slightly non-trivial part is that we want to be able to pull back to a subspace where the amplitude has all plus ones. And so that means that we want this property that if I take normal vectors to any vertex, if I take the normal vectors of any faces meeting at a vertex of this polytope, that all those determinants are plus or minus one. That is a non-trivial fact. So, okay, so that's what we want. But of course, as usual in this business, we're not inventing anything. All these things are just sort of sitting there. So they either exist or they don't exist. But what's remarkable and what we'll now see is that the structure of this quote unquote kinematical spacetime is significantly richer at multi-loop level. And we're actually going to find that these clusterhedron are really naturally living there. Okay, so they're the new features that show up in the surfaces, including crucially these delta-like variables that wind around, are exactly what's needed to solve the problem. Well, there's no problem to solve. They're just sitting there. We just have to see them, but they're actually just sitting there in kinematical space. All right, now before getting to my sort of central example that we're going to talk about in some detail, let me go back and illustrate it in the very simplest thing that we've already looked at. A11, this example of A11, that's actually going to be the smallest special case of the general story that we'll talk about. So let me just let's just illustrate what's happening in A11. So remember, A11, we already saw what the G vectors look like. The G vectors look like this. And then we had the sort of delta in the middle there. Okay. Okay. Let me draw the next one too. Okay, so this was minus 1, 2, minus 2, 3, and this one is minus 3, 2, this one minus 2, 1. Okay. Now, let's already see what the kind of most naive, so this is a two-dimensional space. And so if there was a polytope associated with it, it would be a two-dimensional polytope, right? And if we look at these, if we think about these normals, if we think about these G vectors as being normals to the polytope, we can even sort of start drawing what it looks like. Okay, so A minus 1 would be a normal direction. So maybe we have something that looks like this, right? And then A0 would be a normal direction. We'd have something that looks like this. And then A1 would be a normal direction. So maybe we have something that looks like this. Okay, so we'd have something which where the normals are sort of asymptoting to this something in the direction minus 1, 1. So that's some 45 degree thing here. And similarly on the other side, we would have on the other side, if there was a polytope, we just have the sort of opposite of these. Okay, so if I'm trying to build a polygon, therefore, just from the G vectors that I see, it kind of looks like this infinite thing. So it looks like something that would look like maybe that, and then somehow asymptote to something that's sort of 45 degrees here. That's my asymptote. And then I would have the opposite on this side. Okay. So now already in this simple example, we can ask, why don't I just stop? Why don't I just let's just take the guys that I have in this picture already, And if I take the guys that I have this in this picture already, then certainly, like if I, take this set of vectors, let's say, I can think of those 6 vectors as I can think of them as the normal vectors to some hexagon. Okay, so maybe there's some hexagon that, I don't know, looks something like this. Okay. 1, 2, 3, 4, 5. I'm just drawing it randomly. Okay, so there are some hexagon, and that's it. Why do I need to do anything else? So I can just sort of compactify like that. And even in this 2-dimensional example, so first, I mean, obviously it looks kind of random and arbitrary, but even in this little, it's harder to even do this. It's harder to even do this in general. Well, so long as you have some set of G vectors which together, cover all of space. So I can. So if I say it another way, if I took this example. Then what I'd be doing is the following. I'd be saying this is a cluster cone. 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 Each one of these would correspond to one of the vertices of my hexagon. So there are 4 vertices of the hexagon, and sorry, this is also a cluster cone. So I have 5 vertices of the hexagon that correspond to cluster cones. This is not a cluster cone, but of course nothing stops me from just declaring that there's a sort of a 6th vertex that's associated with that cone and calling it a day. But one indication that this is a crappy thing to do is that even if I did that, and even if I got a polytope, I would not get the amplitude when I pull back to the subspace, because it fails the condition that all those determinants have to be plus or minus 1. Okay, so in fact, if I just go back to the, if I just draw these for the nth time. Okay, so what I'm saying is, let's say I keep this one, I keep this one. Notice that this determinant, so this guy was, this guy is -1, 2. This guy is 2, -1. So this determinant made of these 2 guys, determinant of -1, 2 and 2, -1 is -2. So it's not equal to 1. Okay? So this sort of magical fact that all the determinants are plus or minus 1 would be ruined by this. And notice it gets worse and worse, of course, if I include more and more variables. Okay? So if we go longer and longer, these determinants get larger and larger. These sort of random determinants that I would use get larger and larger. Okay, but there is something else that I could do, which looks a lot more natural, and then we'll see that this is the kind of simplest case of the general story. So first, I stop wherever I want. I keep winding around positively or negatively, and I stop wherever I want. Just not to make it busy, let me stop here and there, but I can keep going however much I want. Okay. So I have these guys. But then what I'm going to do is also add delta. So in other words, I now want to say that I want to think about all of these vectors, including delta as giving me facets of some polygon. In this case, it would be a heptagon, right? I have 1, 2, 3, 4, 5, 6. Together with delta, I'd have 7 normal vectors to this 2-dimensional polygon. So I'm be looking for a heptagon. And what would this heptagon look like? So this is a minus 1, a0, a1, a minus 2, a minus 3, a minus 4. Well, the heptagon would look like I have a minus 1 and a0 would be 2 of the edges, right? 2 of the faces of the polygon, and then a1, and then and on this side I'd have a minus 2 and a minus 3, and all of these are compatible clusters, right? So we have a minus 1, a0, that's that guy, a0, a1, that's this guy, and so on. Okay, so I'd have these. But then what I want to say is that I also have a new face delta, which then completes it like so. So in other words, I want to say that I have a new kind of cluster, which is A1 and delta. Okay, A1 and delta. And on this side, I have a new kind of cluster, which is A minus 3 and sorry, A minus, sorry, I didn't, A minus 4 there. Okay. And so that's the idea. So I have this new face, and I have these two kind of new clusters, quote unquote clusters. They're not normal clusters, but they're clusters between A1 and delta on this side, and between A minus 4 and delta on that side. And but now the one clear evidence that something nice is happening is that the determinant of the A1 vector and delta and the determinant of the A minus 4 vector and delta are both equal to, the magnitudes are both equal to 1. And what is some intuition for this? What's the intuition? So that's the basic idea that we're going to be pursuing, is that we keep all these variables, they keep going, they keep winding around more and more, but we stop at some finite point and we add delta. And the remarkable thing is that delta is sitting there ready and waiting to compactify the space in a beautiful way, so that all the vertices, all the vertices make sense, and that all these determinants are plus or minus, all these determinants are plus or minus 1, and a number of other nice things happen. But I already want to give you some intuition for why delta is that person here. And the reason is simply that I stopped here at this point at A1, but if I hadn't stopped, I would get some next variable over, right? So in other words, let me just draw this picture yet again. I'll draw it a little bit here. So what am I doing? I start with A minus 1 and A0, and then when I mutate A minus 1, I'm flipping this this purple arrow to the other side, right, to get A1. And then I'm flipping A1 through A0 through A1 to get A2, and so on. Okay, so when I've decided that I want to stop here, I've decided, let's say this is the last one that I want to keep, what's the problem? The problem is that there's a certain cluster that was missing. Who was the cluster that was missing? A1 wanted to now, hop past A2 and go over to some A3. And so A1 doesn't have a partner anymore. That's the problem. But what we're going to do is say that once we've decided to compactify and stop at this point, at the point A2, with this winding 2, that anyone that wanted to mutate past that to go to higher winding, instead of having their mutation partner be some higher winding guy that we're not keeping, its mutation partner, it's going to mutate to delta. Okay, so you should think about the partner of A1 is it's not going to A3 or A4 or A5, all those other things for that matter, because that whole stack of guys is asymptoting to delta. So we're going to just say that it's just jumping all the way to a delta instead. So that's the idea, is that we can't naively truncate the whole picture of the clusters, because every variable is mutating to someone else. So if I just decide I'm stopping at winding 10, there's a winding 9 guy that would want to mutate to winding 11. So it doesn't. So that's why we can't just canonically stop. But what we can do is say that everyone who's winding past the maximum amount is going to actually go all the way to a delta. That's the first thing that delta does for us. And you see already in this picture that delta is going to act as a sort of mutation partner for many different people. For example, here, delta acts as a mutation partner for the guys that are winding from the positive side, but also acts as the mutation partner for the guys that are winding from the negative side. So it's going to do double duty and be so all the variables that we're missing are going to get identified are going to have delta as their mutation partner. Okay, so that's already just an early picture for what it is that we're trying to do. We'll see that the delta is doing a number of other things besides. So, okay. Any questions about this before we talk about our sort of central example?
Sorry, Nima, within type D you could have just mutated, right? So, I mean, just one loop. Within one loop,
no, just one loop, everything is fine. Yes, just one loop, everything is fine. Yeah. So just one loop, everything is fine. Although it is interesting that at one loop everything is fine except for this business about tagging, right? So if we didn't know about tagging, then we're also stuck at one loop earlier, right?
Right.
It is interesting that, as I mentioned last time, while tagging looks a little bit funny, purely thinking in terms of the punctures, in fact, tagging is derived from this picture of deltas. So they're not so in other words, it's not really true that one loop everything works and that everything is funny at two loops. Already at one loop there's something funny. We have to extend our notion of what we meant by the variables by adding via tags. And as I explained last time, the tags are secretly these deltas, because I can imagine taking every puncture and just blowing it up to regulate things a little into a boundary component with a hole like that. And then if I have any arc in the upstairs picture, I just have to decide whether it's going to wind around. So again, here's my infinity. So see, this is maybe why you wouldn't want to do it, because oh my God, now I have infinitely many variables. But now that's exactly what we're going to deal with. Okay, but all these, but there is a difference between whether it's winding around in the positive direction or winding around in the negative direction. And you literally get the arcs for the downstairs picture by projecting through delta. So if we project through delta, we go from these we go from this upstairs picture where we've blown things up into the annulus to the downstairs picture with a puncture. But you see that you have to have two different kinds of arc, which remember whether they went around one way or the other way, and that's tagging. So yeah. So in a sense, already at one loop, the fact that we have to do tagging is a foreshadowing of this business of having to deal with the winding and the infinity of the deltas eventually.
But you could have defined the polytope like you guys did in your paper at one loop. Like this Clusterhedra is a polytope which is all loops single trace. Is that that's what was confusing me. The one that you are now defining with a minus 1, a2, a minus 2, a minus 3 was it was not one loop, right? This was going all loops, right? I mean, when you were adding more and more faces to the.
No. This is not it. We'll see what it is in terms of loops. We'll see what it is in terms of loops in a second. Oh, I see what you mean. You mean what is the interpretation of all these extra variables? Is that what you mean?
Yeah, exactly. I mean the.
Oh, great. Yes, because So well, I'll come back to it. I'll come back to it again in the end. But here's the idea. So the idea is exactly. Remember, we don't want all these extra windings are the same variable, are the same loop variable in the end, right? On the other hand, in order to have this whole, I mean, for this whole picture of the triangulation of these punctured surfaces to make any sense, we have to take these windings separately. Okay, so we're going to keep them as separate variables. We're going to make these polytopes. They have all these faces. Of course, they will reflect the fact that, I mean, there's going to be some self-similarity in the structure of these faces, because we're going to see the same structures repeated, just rotated again and again and again. But all of these guys rotate again and again and again. They're all going to be facets of this polytope, just like we see in the simple example, right? And then we're going to chop it off with delta, and we're going to get a canonical form for the whole thing. Okay, so now in the end, you have a canonical form for the whole thing. And now the question is, how do we get the amplitude out of this? And as we'll see, a couple of nice things, a few nice things happen. First, if you do the chopping off in the obvious way, to just keep all of the winding sectors up to some winding, for positive winding and for negative winding, we'll see this more explicitly in a second, then every quote unquote Feynman diagram will be counted the same number of times. It itself together with its winding copies, they'll all be counted the same number of times. Then there is something involving delta. Okay, so what you can do is get the canonical form for the whole thing, and then after you get the canonical form or even the function, you can just manually set all of the winding variables equal to each other. That's one thing that you could do. Okay, if you set them all equal to each other, and actually if you wanted to do the absolute dumbest thing, you set them all equal to each other and then you send delta to infinity. If you do that, you're just decoupling everything that talks to delta, and then you're just getting the amplitude. Okay, so that's one way that literally the amplitude will come out of it. Another thing you can do is to keep this the number of windings is a parameter. So let's say you have W max windings. Okay, like you still set all the variables equal to each other in the function, and you keep delta. So that means that you have an amplitude that has one piece in it that has a factor of 100 sitting in front. If you kept winding up to 100, okay? You have 100 times what you get from summing from what you get from the part where the variables just differ by winding. Now just set them all equal to each other. So I have 100 times the part that you think of the ordinary phi cube theory plus something of order 1 that involves delta. You see, this looks like I'm actually getting the answer for an amplitude for a somewhat different theory, where I've taken the phi cube theory and have weakly coupled it with a factor of 1/100 to this other sector of delta. Okay, so that's, I think, the most natural way to think about it. This parameter that counts the amount of winding is like a coupling constant. It's like a constant that tells you how weakly coupled this delta stuff is. Okay, now, and as we'll see in the small examples, delta looks like gravity. In other words, I mean, we don't have spin here, but delta has the flavor of something that's universally coupled with no color, which talks to everybody. And even when we factorize on delta equals 0, we factorize in just the way you would expect from, we'll draw the double trace diagram. We factorize in just the way we see the closed strings emerge in open string theory, that you have the particles on the outside annulus produce this delta as a propagator and give you the things that are the internal annulus. Okay, so, but I don't want to say much more about that now because we don't know if that interpretation holds very generally. What I can say is that the natural thing to do, since the winding is a parameter, is you go to some W max, you stop there, you set all the x's equal to each other, and so that gives you an interpretation of the phi cube theory that you like, plus another sector, weakly coupled to another sector. And this other sector doesn't have color, it doesn't have ordering, really smells like gravity. Okay, but we're not sure. We're not yet sure if it's gravity or if it needs to be interpreted in another way. Okay, so that I think is the most in a sense the most interesting part of this is that we didn't want this delta, but without the delta we can't have a sensible polytopic story. And with delta we can, but that forces the existence of some other stuff that's coupling to our biojoint phi cubed amplitudes. And it would be really interesting to try to interpret it and figure out exactly how to think about it. We don't know yet exactly how to think about it. But as I said, it definitely plays this role of universal coupling. And we'll see that in more detail as you see what the clusterhedra look like. Did that answer your question?
Yeah. Just one small thing. So just following from your paper, Song, and your paper, this is the previous example is the two particle, the one that you were drawing above in the plane, the A1 A-1.
Not quite. We'll see what that one's a very degenerate example. It's a double trace
Okay, okay.
With only one. Yeah. Yeah. Just,
I thought it was just a
horses. It'll be clear what it is in a second.
I see.
Yeah.
I thought it was just at one loop. It's just a square, right? In the polytope will just be A1 cross A1 in the one loop case.
Yeah, but that is not this guy. That's right. Yeah. So one loop. D2 is exactly A1 cross A1 as you said, but that is not this. So this is actually this is a double trace one loop thing. It's not a single trace one loop thing. It's an annulus.
I see.
It's an annulus and not a surface. Yeah, I'll
okay. Thanks. Yeah.
Okay. All right. Any more questions? All right. So in fact, I'll close just by talking about this one example in some detail, and then I'll tell you a few other things and where things stand and where we're going. So let's say I'm interested in one loop double trace diagrams. Okay, so double trace diagrams. So this is subleading in N, but double trace at one loop would be given by triangulations of this surface. Okay, so just an annulus with n points on the outside, n1 points on the outside, and n2 points on the inside. So we can call this surface A, n1, n2. By the way, you can also interpret this as an all-loop cut. Okay, so if I just take planar diagrams with L loops on the inside, but I imagine that I actually have I have a class of diagrams where the L loops where I'm cutting the internal loops between all L of them, then doing that is like doing that is like adding already a lot of arcs in this in any triangulation that I would draw. So restricting myself to that cut is restricting myself to drawing some of these lines in here already. Then I would triangulate the rest of the surface. Sorry, and even draw other ones inside here. But anyway, then I triangulate the rest of the surface, and doing that is again giving me the same annulus. And so I can think about these annulus diagrams as calculating double trace at one loop and a certain class of cuts of the L loop amplitude for all loop order. Okay, so I can think about the n of the inside annulus as the number of loops, and I've gone on this particular cut. Okay, so this is already giving us access to non-planar and all loop order information. Okay, so now what I want to do is actually go back and think again like we did right at the beginning. Okay, so now forget all this cluster stuff. We're just going to go all the way back and just think about the kinematic space. What are the variables and what we can start doing as far as a kind of dynamical question in kinematic space. All right, so to begin with, here is one class of variables which go from which I'll call out or in, where the arcs go from either I on the outside to J on the outside, or the other way around. So here I've just drawn the out ones, and here I have two kinds of variable. I have xij. Note again, xij is not the same as xji because they can go around the annulus in two different ways. And also, I have what I can think of as a self loop, xii. In general, I'll have xii, or I'll call it xii plus n, which is just that self loop. And I have the analog of these guys just on the inside as well. So I haven't drawn them. So I can have these xij's like this, and I can have the analog of these self loops like that. Okay, that's one set of variables. Now notice that these variables don't have any winding associated with them. Okay, there's no I can't wind around the annulus and go back to the outside without the arc intersecting itself. Okay, so these variables don't have any winding. These are the variables that do have winding. You can call them the in-out. The in-out variables, and they well, just as I've drawn and I've seen examples already. So they're labeled by some winding number, and they wind around the annulus some number of times. Okay, so that's my kinematic space. Okay, just my kinematic space is My naive kinematic space is the space of these xij not equal to xji, including these xi posends, as well as these x little I big I's that are labeled by some winding, okay? Positive or negative winding. Now, as we've seen already, this variable delta is going to be a crucial part of the story. Okay, so we're going to include this loop, and this loop is, as we said already, is not a cluster variable, but it's going to be a crucial part of the story. And just as in our previous examples, it has the property that for positive winding x's and for negative winding x's, it's delta that increases the winding. So delta gives me more positive winding, and delta also gives me more negative winding. Okay, and by this simple formula. Okay. Now, what happens in this example, in this this A n1 n2 APQ example, is again all the g vectors asymptote, all the winding g vectors asymptote to a delta. Okay, just like we saw in our simplest example. And let me show you just how it works in A21, just a slightly bigger example than the one that we saw before, because it has a few moving parts that are more moving parts that illustrate the generic situation. We didn't quite see everything in that A11 example. What we're seeing now in this A21 picture is basically everything which is relevant to the geometry of the G vectors and the story of the polygon. So let's review who the variables are for A21. So here's A21 up here. So here's two guys on the outside, one guy on the inside. I have this variable A. There's A0. Then I'd have A minus 1. You know, I'd have well, I have all the winding eyes that we talked about before, but I also have these two loop variables. This one here, that one there, which I'm calling U, because it's anchored to the up guy, and this guy here that I'm calling D, because it's anchored to the bottom guy. Okay. All right, and so you can just compute all the G vectors, and I'm just going to tell you what the answer looks like. Now, the G vectors are three-dimensional vectors. This is a three-dimensional algebra. This is a three-dimensional space. The dimensionality of A, P comma Q is just P plus Q. Okay, so it's a three-dimensional space. So let's look at so I should draw some three-dimensional vectors. I'm not going to draw the three-dimensional vectors. I'm just going to draw sort of the projective version of the three-dimensional vectors. In other words, I'm going to imagine looking at the ray from those three-dimensional vectors and where it intersects a plane. So that's how I'm getting a two-dimensional picture for a subset of the G vectors. For the subset that I'm the subset I'm going to be interested in illustrating. Remember, the G vectors sort of span the whole space. So I have some set of G vectors in this direction, and then some set in the opposite direction. I'm going to slice with a two-dimensional plane, let's say in this direction. So I'm only going to see, I'm going to see the G vectors pointing in this way, but this is where the infinitely many of them will live. There's a finite number of ones pointing in this direction, let's say from the initial basis, but all the other ones I'm going to see by intersecting with this plane. So it's easier to visualize by drawing it in a two-dimensional plane. And this is what it looks like. So this is the two-dimensional projection of these three-dimensional G vectors. So you see they have this cool feature. So first of all, I have this kind of line. I have this line here. And this line, again, in the three-dimensional spaces is a plane of the actual G vector. So there's some plane in G vector space. And you see that all the positive winding variables are on one side of this plane, and the negative winding variables are on the other side of this plane. Okay, so here I have A2, B3, and here I have A minus 1, B minus 1, B0. The positive guys are on one side, the negative guys are on the other side. Also, interestingly, on this plane, I have exactly the non-winding variables. So this U and D precisely don't have winding numbers, and so they live on this plane. And delta has a very privileged role in this story. So delta is the middle of this picture. Now, what happens is that as I go to higher as I go to higher and higher winding, remember, I'm taking every vector and I'm just adding delta to it. So when I go to, when I do this two-dimensional projection, it means that I have some vector, I add delta, that just means it's going closer to delta. I add delta again, it means it's going closer to delta. So as I wind, all the vectors are moving in towards delta. And that's what we see in this picture. So I started off here with, let's say, A2 and B3. Now here is A3. A3 is getting closer to delta. B4 is getting closer to delta. All of them are getting closer and closer to delta. Okay? And in fact, if I draw what the cluster cones look like, you get this. You now get another sense for what it means that these cluster cones are tiling, non-overlapping tiling, but asymptoting to a delta. So this is what it looks like. Everything that's shaded in here is a certain cluster cone. For example, this kind of cone, A2, A3, B3, this is from this type of triangulation. So I can start with this triangulation. So let's say A0, A1, and B1. So that's a triangulation of the surface, and then I can just wind it. So that's not the first thing you would draw, because every loop is looping around more, but I can take this picture and I can just wind the inside annulus as much as I like, and I get higher and higher wound versions of the same triangulation. So here's one of them involving A2, A3, B3, and then there's a cousin where you swap the A for the B, so that's A3, B3, B4, and then there'd be the next one here that would add yet another small triangle on this side, and so on. Okay, so add yet another small triangle on this side, and so on. Okay, so those are those set of cluster codes. What about these ones, like D, B3, B4? What is that? That is this kind of triangulation, where I take, there's D, let's say B3 and B4, where I wind around one more, okay? So that is a triangulation. Well, I didn't do it with 3 and 4, but anyway, it's a D and two Bs. And so you see, here the D always stays fixed, and I'm just continuing to rotate the Bs on the inside. That's a lot like the triangulation of A11 that we saw before. Putting this D on the outside is sort of blocking us caring at all about the second point there, and then the story that we get is just what we saw for A11 before. So this triangle, next triangle over, the next triangle over are those clusters. And so you see what's happening. This set of G vectors is asymptoting to delta. The triangles are asymptoting to delta, but again, we never quite reach delta. Delta is this special point in the middle.
Sorry, Nima?
Yeah.
Is there variable like x12, x21?
No, we don't have x12, x21 in this example, because those are homotopic to the boundary. Okay.
Oh, okay, right.
So yeah. So I forgot to say. I mean, I gave you the sort of generic rules here for the variables. That's for generic n, but for a very small n, like we have in this example, this variable is not a variable because I can keep deforming it until it becomes the same as the boundary condition. Sure. Any other questions? Okay, so just to summarize again, the set of all the G vectors is really for the winding guys. But all the G vectors have the following property. They're the guys that are not winding, and the ones that are not winding actually live on one lower dimensional plane in this whole space. Delta is like the middle of this plane. Delta is a special point inside this plane. Then I have the positive winding guys and the negative winding guys, and all of them are asymptoting towards delta, and all these cones are non-overlapping and punching in towards delta, but again, leaving delta uncovered if you stop at any finite. Okay, so that's a picture of the variables, and now what I want to do is go back and just think about what our kinematical spaces look like, what these kinematical spacetimes might look like. Again, just thinking by analogy with what we did before for the case of the icosahedron. Okay. So first, let's look at these variables xij, xi capital J. These in-out variables that are winding. Okay, these in-out variables, these guys, these have a kind of a cool kinematic space. So here I'm following my nose, just what we did before. We start with one of the variables, let's say x1 1 dot. Okay, and then I'm going to, in order to write them all down, I'm just going to translate each variable by the cyclic shift. Okay, so and again, remember, because the shifts that I'm doing are compatible with the orientation of the surface, when I do a cyclic shift, I'm shifting on the outside in one direction, on the inside in the opposite direction. So anyway, if I write them all down, if I call the internal variables dot and the outside ones without a dot, then I have 1 1 dot, 1 2 dot, 1 3 dot, 1 4 dot. And let's say there are 5 things on the inside. So I've come back to 1 1 dot. But you see, what have I done? I've taken this variable with 1 here, and there's 1 dot. So I've taken 1 1 dot. Then I've rotated 1 dot over. So now it's 2 dot. Then I've rotated it to 3 dot, then 4 dot. And now when I come back to where I start, I've wound around 1. Okay, so I've come back to 1 1 dot, but I've increased the winding by 1. Okay? So when I just do this exercise of taking the variables and just what we did before for the icosahedron and just drawing them on a piece of paper where the variables that I see are what I get by applying the cyclic shifts, then in this direction I come back again, but I don't come back to the same variable. I come back to the variable with winding number plus 1 more, and so on. So I get 1 1 dot with winding 1, 1 2 dot with winding 1, and so on. Okay, so in this direction, I just have this thing that goes on forever. Now, what about in the other direction? Well, the same thing. I'd have 1 1 dot, 2 1 dot, 3 1 dot, and then I'll come back to 1 1 dot again. Let's say I have n equals 4 on the outside. So I come back with 1 1 dot again, but once again, I've come around with winding number 1. Okay, so I've just done it in the opposite way. 1 1 dot, 2 1 dot, 3 1 dot, 4 1 dot. It comes back, and now I have something that has winding number 1. So, and that's it. So I just keep doing that forever. Okay, so if I make this sort of infinite grid, this infinite grid is the analog of our infinite strip in our discussion of the icosahedron. But this infinite strip has a slightly more interesting identifications on it. So you see that this guy here is 1 1 dot with winding 1, which is the same as 1 1 dot with winding 1 here. Okay, and so in general, if I write this infinite grid like this, it divides up into winding 0 sector, winding 1, but I also have a copy of winding 1 here, winding 2, but a copy of winding 2 here. Okay, so if I want a non-redundant covering of the whole thing, I can just keep all of these guys. Okay, so it's infinite. Winding 0, winding 1, winding 2, but it's a cylinder. It's topologically a cylinder. And I can just keep a copy of all of them, just this copy as I've done here in the strip. But if I write it in the strip, I have this identification between the top boundary and the bottom boundary in exactly the way I have drawn. Okay, so this is a non-redundant way of covering this in-out kinematic space, and I've drawn it again here. It's just this green region where these are different sectors with winding 0, winding 1, and so on. But I have to identify the points on the boundary in exactly the way that we've indicated. Okay, so already I'm using our kinematic space for the case of the our kinematic space for the icosahedron had this sort of Mobius symmetry reflecting xij equals xji, and then we took a chunk out of it. Now we have something different. Now we have this infinite cylinder. The infinite direction is winding, right? But just exactly as previously, once I draw all these things, I'm invited to look at something that looks like the wave equation, time evolution, exactly the same things that we talked about before. I make some choice of initial cluster, some choice of initial Cauchy surface, let's say that one, and I use it to evolve everywhere into the future, just like we did before. So we're writing down exactly the same equations as before. X plus x minus x is given by this constant. Okay. All right. So this is our. So there's a. What I'm saying is that there's a natural kinematic spacetime associated with these out-in variables, and a natural analog of the discrete wave equation for them. So we're gonna take those. All right. Now, what about the rest of the variables? We have the in and the out kinematic spacetime variables too. And these are also quite simple. So let's look at this example. I'm just going to look at the out ones, let's say. So I would say start with, let's say, x13. So there's x13 here. Then I'd have x14. There's x14. I'd have x15. There's x15. And then again, I'm doing the same thing always, right? I'm starting with one variable and just acting with the action of the cyclic symmetry on the other one. So then I come back to x11, okay? And that x11 is that loop which we're allowed to have. So I'm going to call that 11. I could have called it 16, but I'll just call it 11. It doesn't have any. It's not ambiguous. All right. And so and as before, 12 is equal to 0. Okay. So 12 there is equal to 0. And then I keep going. I complete the whole picture, and again I get something that looks like a kinematic spacetime. Now, as familiar from before, we still have these 0 boundaries on one end. We don't have the analog of the 0 boundaries on the other end. Instead, we just have these variables 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. And this chunk here that I've drawn, again, covers all the variables that we see once and only once. All right, so we have a kinematical spacetime for the in-out variables, which are these infinite cylinders with the winding, and we have this kinematical spacetime for the in and the out variables. And we're always going to do the same thing. We're always writing down the sort of wave equation, the Gauss's law wave equation for the sort of smallest meshes in these pictures, the smallest pixels or meshes in these pictures. All right. So I hope you see this is really the kind of precise analog of what we did for the case of the icosahedron. We just look at what the kinematic space is. There's some slightly interesting identifications or structure to the kinematic space, but we always get this grid-like structure in the kinematic space, and we always write down this discrete analog of the wave equation. Okay, so far, so good. But we have the problem. We still haven't solved we haven't dealt with the issue that we have infinitely many winding variables. And
sorry, Nima. Yeah. So how do you connect these two grids now with the grid you had shown, I think, towards the end of last lecture with for the one loop with the fork-like structure, you know, in the kinematic space-time?
Yeah. So they're as you see, they're very closely connected to each other. But there we saw the
you'll come back to that then.
I'll come back to this point.
Okay, thanks.
I will come back to this point. So, but maybe I can say it now. There's going to be a boundary of this space where once we have this delta, it's natural to ask what the face looks like, what the delta facet looks like. And geometrically, the delta facet has to do with kind of shrinking, with shrinking the loop around the inside annulus to 0 size. And so what you get from that, from the perspective of the outside ring, is something that looks like diag, right? Because now it looks like a puncture. Similarly, actually, from the perspective of the inside ring, you have something that looks like a puncture. And so the delta facet is almost the direct product of the dn on the outside and the dn on the inside. It's not quite that, but that's at least the first picture for what it is like this direct product of the dn's that you see from the outside and of the dn's that you get from shrinking the annulus to 0 size. That is so dn is sitting inside this guy. In fact, the dn cross dn is sitting inside this guy, but it's a somewhat truncated version of dn cross. That gets in a little bit into details. You don't see it. You don't see the dn so obviously in the other faces, because because this is a double trace at one loop, and so the kind of forward limit interpretation of the double trace is different than it is for the So in other words, this is one loop. This is double trace one loop. dn is single trace one loop, and so we don't sort of simply see a cut of one yielding the other. If I went to two loops, you would see dn directly. And we'll talk about the two loop at the end. If we went to two loops, we'd see it in a much more straightforward way. A particular cut will just reveal the dn literally one loop in the forward limit. In that.
So this point 1, 1 is not like the pair of points that you had in the earlier causal diamond, the 1 and 1 tilde.
No, it's not a pair of points. It's just one point.
It's just one point.
Exactly. It's just a single point. Yes, exactly. Oh, sorry. That's what you wanted to clarify. Yes. Yeah. Here it's just a single point. Yeah. That's right. If you know about this stuff, this part of the story is actually gives a realization of the halohedron.
Okay.
So in fact, the halohedron does have a purpose to, it's kind of a little funny to have two pictures at one loop, and what is the purpose in life of the halohedron? But the halohedron is actually sitting there in this part of the picture. Okay.
So delta is like the UV tadpole, that the cyclohedron phase of the halohedron, the delta going to the delta phase.
Not quite. This is just a delta going to 0 is kind of like 2 copies of D or 2 copies of halohedra, but you have to say, or 2 copies of halohedra, but you have to say a little bit more. And so I don't want to get into that now. But what I was saying is a more precise statement that if you just look at these in variables, you just take them, you just take these relations, you see what polytope you get from it, you get the halohedron.
Mm-hmm.
But it's not the whole story. Okay, so let me. Okay, so far we've seen that. Yes.
So the wave equations that you just mentioned, are they the same as that you showed earlier by the modification where you added NW in the coefficients?
No. Here they're all just the most boring normal wave equation. X plus X minus X minus X equals C. Precisely what we saw before.
Okay, but aren't these for the one loop calculation now? The wave equation.
Sorry?
Aren't these wave equations now for one loop
they
level?
Are for this single trace thing at one loop, but even in our previous story when we were doing dn, these were always X plus X minus X minus X. There were never any numbers there. What happened in dn is that sometimes on the right-hand side you could have 3 minus X's. But we could have X plus X minus X minus X minus X, but there are never any 2s.
Okay, thank you.
Okay, and that's
sorry.
Yeah.
So when you see dn inside this example or 2-loop example, do you see the antenna, or you're really seeing? Of
course. No, we know. In this example, the way you see dn is much more subtle. So let me not talk about that. It's not literally
but for 2-loop you will see it.
For 2-1, literally, absolutely. But that's because in 2-loop, already in 2-loop already we see the in 2-loop already our triangulations. Our variables will have the tags in them and everything. Of course, we'll just direct the end. The cool thing is that even if we didn't know about tagging, if we started with but this is the slightly more subtle part that I don't want to spend time on now. But at least roughly, if you blow up all the punctures to these little annuli with points in them, then there is a face where you send that delta to 0. And so if you do that just where the inside guy just has 1 point on it, then you do that, you go to the delta facet, and that actually shows you the tag and the untagged variable. And so from there, you would literally see the again, literally dn if you did that. So there's a way of getting the triangulations of a surface with 1 puncture by the thing that we're talking about. with just one point on the inside and shrinking it to a 0 size, and then you would literally get dn. You would get the dn by seeing, but you see the tagged and the untagged variables from the positive and the negative winding sector. Okay, so the fact that there are two variables would show up in the fact that we have the positive and the negative winding.
Sorry, Nima, can I ask us one more? So your equation was x winding plus delta was the x minus winding for the, right, the equation relating the plus
like
winding.
The one that I've drawn here?
Right, exactly. So in the, just wondering in the, oh, I see, it's +1. So it's not the, so this, in the notation of your paper with Song at the one loop, this delta is not like the y0. It's not correct.
No. The delta is like nothing like, yeah.
Okay,
this
okay.
Delta is just, yeah. This
Okay.
delta is not like, like anything before. Yeah.
But the x plus w, I can think of that as yi and x minus w at yi tilde. Is that okay? Is that for one loop? For one loop. For w equal to 1, or even that's not the right.
No, not quite. I think.
Okay.
No, yes. So that is basically correct. Okay, because what I'm saying is that in the case where there's just one hole inside and there's just one point on it, then the tagged and the untagged variables are the ones which you're winding around one way and winding around the other. Okay? But again, it's very important that these winding formulas are sort of they're asymptotic. I mean, what I mean is that it's not true that I start with negative and I keep adding delta and I get positive. It's not like that. I have these guys, I have something slightly positive, like 0 or 1, but early, and then I add delta and I get all the rest of them. And then the one right before it is not related, but I add delta and I get all the ones on the other side. Okay, so in this upstairs picture, we have all this winding. But notice that since all these winding variables differ by adding by delta, just geometrically, if I project through delta, they would all end up on the same vector. Okay? And similarly on the other side. So the y and the y tilde are actually the ones which have big positive winding and big negative winding. And when you project them, they turn into y and y tilde. Exactly.
So delta relates m loop variables to m plus 1 loop variables. That's why there's no analog in the, because x.
No. It has nothing. I mean, delta, again, all of these things with different winding represent the same loop variable.
Sorry. Yeah. Okay.
Right. So in a sense, all of this delta is about this funny thing that all of these arcs are encoding the same loop variable.
Okay. Yes.
Okay. Any other questions? All right. So now we're actually going to come to the so far. So this is basically straightforwardly mimicking the things that we did before. So we have the in-out kinematical spacetime, the in-in kinematical spacetime. We have the wave equation picture. But now we have to deal with this. Now we have to deal with the infinity. And so what we're going to do is we're going to compactify these winding sectors with delta. Now remember, we have I told you that the kinematic spacetime is this infinite cylinder. It's really two infinite cylinders. One cylinder for positive winding, another cylinder for negative winding. So to begin with, I want to deal with the problem that we mentioned before, that as we go, I want to truncate. Say I'm going to only keep up to winding 10. But the problem is, okay, that's fine. There's a winding 9 guy that wants to mutate to a winding 11 guy. What am I going to do with those? What am I going to do with those relations? In other words, in my wave equation picture, there were formulas that were solving for the winding 11 guy in terms of the winding 9 guy. There's a formula like x11 plus x9 minus x10, something like that, is equal to some right-hand side. And the question is, what am I supposed to do with that relation now? I want to compactify. So now I've lost x11. What am I supposed to do with that relation? So that's what I've written down here. And the answer is very simple, is what you do whenever you see this relation involving someone that is beyond your winding cutoff, you just replace it with this one, okay? You just replace it with x winding plus delta minus x winding plus 1. See, this is exactly the relation that you would get from the top one if you just wrote the formula that x winding prime is equal to x winding minus 1 plus delta. Okay, so if you just literally took this formula and you used it, you just expressed the variable that went too far in terms of variables that you keep plus delta, you would get this relation instead. Okay? All right, so that's the first idea. Then we're gonna go up. We're gonna in our cylinder for the winding variables. We're gonna stop somewhere, and then all the dangling things near the cutoff, we're going to just write the relation x winding plus delta is equal to x winding plus 1, where all of these windings are inside. All of these ones are the ones that we have kept. So we're going to do that at the top, and we're going to do that at the bottom. Okay, so that's the first thing that delta does. Now there's something else that we need to do, which is that we describe these two different kinematical spacetimes. Right? There's one involving the in-out variables. Right? We have this cylinder involving the in-out variables, and then we have these involving the in-in and the out-out variables. And but they clearly have to interact with each other. These two different kinematical spacetimes interact with each other. They're in triangulations together. I mean, we have these variables definitely have to talk to each other. So so we somehow have to find some relations that we're going to write between the in-in and the in-out variables. Okay, so so in other words, we don't have any sort of a priori obvious kind of space-time picture now for relating the in-in and the in-out variables, because they have different symmetries. You know, one of them sees both the shifts on the outside and the inside, whereas the other one only sees the out-out or the in-in shifts. Okay, and so so there has to be some new set of relations. And these are the relations that turn out to give us the object we want, but there really are the sort of, I don't know, I think they're the most natural ones that you could imagine. Is that you just take these variables on the outside involved. So I need to find some relation between an in-out variable, which has two labels, a j, a little j and a capital J, and the other one. Okay, so this set, where you just look at the relations that you get between x, these loops xii, and the in-out variables, these are the only ones that you write down. And in fact, since we're only keeping the maximally wound, we're keeping up to some winding, you only write these relations down for the maximally wound guys. Okay, so the sort of picture that you should have is you have the cylinder and all these variables. You have this in-in and the in-out, and then near the top of the cylinder, first we have this thing where we have to figure out what happens when you jump too far. So there you add delta. Next, we have to have some way for the top and for the out variables to interact with these things. We're just going to have them interact at the top here. This is reasonable because the out variables don't know about winding. So they're just going to take the one that they see from the maximum winding, and they're going to talk to them simply via relations of this form. So xii plus x little ji for the maximally wound guys and the maximally negative wound guys, and whatever you get on the right-hand side. So whatever you get from the right-hand side is what we get from the from these mutation relations. I'm not going to write what they are. It's sort of simple to write what they are in general, but it's these relations that we keep. Okay. All right. So so that's how we glue. That's how we glue the in and out to the cylinders, both to the negative cylinders and to the positive cylinders. Finally, and this is in a sense the most non-trivial thing of all, is that we have this sort of positive winding sector and this negative winding sector, but we have to glue them together to close the whole space. That's what we saw in our simplest example, right? In the A11 example, we have the guys going around like this, we have the guys going around like this, and then delta allowed me to glue positive to negative winding together, okay? The remarkable thing is that there's always a relation of the following form between the G vectors, and therefore we can think of it as a relation we can think of it as one of our extended wave equation like formulas. And the relation is simply that you take any variable, any given xii variable, and you look at its maximally positive wound version and its maximally negative wound version, And the relation is that in order to glue positive to negative, you just say x plus x minus is equal to something times delta. The number, the numerical factor in front of delta depends on how big the winding is. But however much you wind, it's roughly the sum of W max for the positive and the negative. Okay, so the more and more you wind, the bigger and bigger this coefficient in front of delta has got to be. But that is the relation. That x plus x minus is equal to something, that involves ordinary other loops and so on. But this is not a mutation. This is something involving very, very far away variables from the perspective of the cluster algebra. After all, I've sort of taken some of these variables, I've mutated a huge amount to increase winding in this direction. I've mutated a huge amount to increase winding in the other direction. So there's not remotely a standard relation or standard mutation that connects the positive and the negative together. But the sort of hint that there is something that wants to connect them is that in the G vector space, there is this plane where the non-winding variables are, and the positive and negative variables are actually approaching each other from opposite directions on that plane. So that's why it seems very natural to give a relation between them. If I give you the version of this picture for delta, for the version of what we're doing here for A12, remember I told you we have all these variables. Well, let's say that I decided to stop literally just at this relatively small amount of winding. Okay, if I stop here, I'm saying that there's a relation between the positive and the negative winding variables. For instance, I have that B3 plus B0. This is the maximally wound B. B3 plus B0 is equal to D plus delta. Okay, so I have this quadrilateral, and so I have that relation between the most positively wound B and B0, is the most negatively wound one here, is equal to D plus delta. This is not a standard mutation, but it's a relation which is true, and this fact that there are actually relations between oppositely wound guys is what makes it possible for delta to cap off the whole space. So that's a sort of a non-trivial fact. So that's what I've said here. The existence of these relations is non-trivial, and is but the fact that they're there is really the way the surface cluster algebra is telling us to use delta to give us this compactification of the cluster complex. And so that's it. That's the full kinematical space-time picture now for this annulus problem. So I can summarize it. So our kinematical spaces had this in-out part that was a cylinder. Here I started with some initial Cauchy surface, quote unquote, and I evolved. So that's in-out for positive winding. I also had in-out for negative winding. Okay? So we have these relations that glue the out-out. Meanwhile, I have out-out and in-in that are just their own private kinematical spaces that just look like these squares. And then I have to have things that glue them together. So what glues the out-out and the in-in together are just involving these maximally wound guys. So I go up winding however much I want, but involves these relations involving maximally wound guys. And I have the same ones on this side. So I've just copied the picture of these in-in and out-out kinematical spacetimes on the other side, just so I can draw it. So I have these relations. And then finally, most interestingly, delta allows me to glue everything together. It allows me to glue the positive and the negative winding sectors together. So in this way, it's sort of gravitational. It couples everyone that otherwise don't have any relations between each other, sectors that wouldn't talk to each other. With delta, we can write down these simple relations that takes any point in here and identifies it and writes down a relation with its friend over there with opposite maximal winding. Okay. All right. So that is a description. Now that whole kit kat and caboodle gives you some polytope. Okay. So there's actually some novelties here as well that I don't have time to talk about. Remember, in the case of ABHY, we just take these basic relations. So the claim was of all these linear relations we have in the of all these tropicalized linear relations, that we can express all of them in terms of a particular basis set. And that basis set turned out to be the little pixels in the space-time, in the kinematical space-time. So that's a cool fact, that if you write down any of these other relations, you can generate all of them in terms of the ones that you sort of see in terms of these small pixels, the small meshes in the kinematic space-time. Well, the same thing ends up being true here. So if you just take all of the relations that we see in this extended kinematical space-time, including the new ones involving delta, then if you look at all the relations there are, so I told you that these relations between positive and minus are not mutations, but if I take any two arcs on the surface and these arcs cross each other, then I can use those skein relations in order to get some relation between them. So I know if I just draw the arcs on the surface, there's a gigantic set of relations between them. Some of them will intersect once. The ones that intersect once are mutations, but they intersect any number of times. And in fact, the ones that involve huge winding on one side and huge winding on the other side intersect a massive number of times. But for every such pair of arcs, I can write down some relation. Okay? Every such pair of arcs is associated with one of these linear relations. So I can take that gigantic set of relations between all the arcs and ask, is there, stop it somewhere. I stop at some maximal winding. For all the relations that would involve someone that went too far, I replace it with this relation involving delta. And now I have a well-posed question. In this humongous set of relations, what is the basis set that generates all of them? And the answer is exactly this kinematical spacetime. So we see that we can, as we did in the association, but now this is in an example with more moving parts, we can either just begin by writing sort of simple things down in kinematical space to see what we see, or we can ask this sort of principled question. Let's look at all the relations there are between arcs on the surface and see what is generated by them. And the answer is the same. It's this kinematical spacetime is a way, and the relations we see in this kinematical spacetime, including these funny ones, including these funny ones that glue the kind of different regions together, as well as the ones involving delta, they're actually the sort of basis generating set for all. But in the case of the association, once you find that basic generating set as a ABHY, you simply, to get the polytope, you simply take all those relations and you set the right-hand side equal to positive constants. What happens in this example is that in general, you have more relations than needed to give you the correct dimensionality of the space. So that means that these relations are actually, that means that while these relations are the basis for positively generating all of the other relations, if I simply set the right-hand sides to constants, I have more relations than I need in order to define a polytope of the correct dimensionality. And in fact, there are linear relations between them. Of course, the linear relations involve minus signs, but there are linear relations between all these guys. And so that means that to get the polytope, you have to simply set all of the constants to positive values, but those positive values have to satisfy relations. And so what that means is that the constants that appear on the right-hand side of these ABHY-like equations, instead of just being positive, have to live in their own private polytope. And so there's yet a separate polytope here, which is a polytope that controls the right-hand side of the constants in these ABHY realizations. So that's another sort of new thing that happens, is that we have to that these constants have to live in polytopes rather than simply living in simplices that say they have to be okay. So all right. So I think that's all. So I think that's the degree of detail that I think I can get into for this example. But let me now just close by telling you what the sort of general state of affairs is. So these examples with a single delta, there's really sort of two examples of them, and they're affine versions of the finite type Deacon diagrams that we talked about before. So you can think of these as the affine clusterhedra, and this APQ is one example, And another example is a dn tilde, which is 2 loops. Okay, so just two punctures. In both cases, it's a single delta. The one that we talked about now, in the case with 2 punctures, the one that winds around the 2 punctures. Exactly the same ideas work for dn for d tilde for the 2 loop planar amplitudes. So we have clusterhedra for 2 loops for these single trace 1 loop, these double trace 1 loop, and which you can reinterpret as this particular all L cut. Okay, so all loop order cut. In all these examples, delta is the mutation partner for every missing variable. Every vertex, this means that every vertex, including the vertices on delta, you can actually unambiguously associate with a diagram. It's just that the delta would be a different variable in different diagrams. The delta is the sort of mutation, the missing mutation partner for anyone. So all the vertices can be unambiguously associated with diagrams. And if you do the obvious thing, you start from your initial cluster, and then you just keep you just keep one winding copy of everyone and stop. Then you can see it's slightly non-trivial. It's not that non-trivial. That all the vertices that don't sit on the delta facet are counted exactly the same number of times. Okay, so that means that in the canonical form for the whole answer, there's a piece that doesn't have delta at all, and that piece just looks like many copies of the Feynman diagrams. That will give you like many copies of the diagram. So if we set all the variables equal to each other at that point, we'll just get a big W max, the big overall winding multiplied by the phi cubed amplitude. And then, as I was saying before in answer to Alok's question, then there's a part that involves delta. And that part looks like it's sort of some sector involving this new delta, new poles involving delta that actually that are interacting with this biadjoint phi cube stuff. If you wanted to, you could send delta to infinity, and then you'd just be left with the amplitude that you want. But I think it's clearly interesting to keep delta around and try to interpret what it might mean. Whatever the delta is not colored. It interacts with everybody, and it has other properties I've said a few times that are roughly reminiscent of gravity, but we're trying to understand what the precise statement is. Another quite non-trivial fact is that all of these determinants involving all the determinants of the normal facets, including the ones that involve delta, they're all plus or minus 1. So that when we pull back to the subspace associated with this clusterhedron, we get the amplitude with all plus 1 coefficients. Okay, so here's a picture of the clusterhedron for A21, for that 2-dimensional example that we talked about. You see there's this delta facet, and let me not go through this in detail. Just you see that there's a concrete 3-dimensional polytope associated with this example. All right, so okay, so we're done through 2 loops, some all loop cuts. Oh, sorry, let me say there's one more example. They're actually just in the middle of finishing understanding. There's one more example that has a finite number of deltas, which is kind of cool, which is 2 loop double trace. Okay, so this is the sort of last simple example, simple in the sense that there's a finite number of deltas. In this example, there are 3 deltas. There's this delta, there's this delta, and there's that delta. Okay, and again, if you're roughly thinking about there are 3 deltas, and we're in the middle of finishing the analysis for this guy, but it looks like it's basically the same story. Okay, so, all right. So I want to tell you about some more interesting things that happen. Well, there's a strategy for what to do for any surface, any number of loops, all orders n1 over n, is to understand these decoupled winding sectors or these topological sectors. Think about their kinematical spaces privately, and then make them talk to each other by using these deltas that are closed loops on the surface. And these deltas need to somehow couple all these winding sectors, all these topological sectors that would not otherwise interact with each other. So in this way, again, sort of gravitationally couple all the sectors together. So that's the basic strategy. And just to give you an idea of what new things happen when we go beyond these affine types. So it seems that the central novelty beyond affine type is that in all these examples that we've seen so far, the kinematical space was static. What I mean is that well, you just draw something that looks like, in other words, in this analogy, it looks like flat space-time. I just have a grid, and I can have more or fewer points, but it looks like I'm covering something that looks like flat space. Associated with that, despite the fact that the cluster algebras are infinite, you can kind of ask for the rate of growth of the number of cluster variables that you encounter as you mutate. And the rate of growth is just polynomial in these examples. Okay? So they grow, but basically I keep mutating, which means I keep winding around some more, and if I mutate more, I wind around more, but it just grows polynomially with the number of mutations. The real novelty beyond this is that these kinematic spaces are cosmological. They grow exponentially, and they, even in the simplest cases, they look a little bit like de Sitter space. Okay? So for example, if I look at, this is an example that we understand pretty well. Let's look at once punctured torus. So here's a torus. I've drawn a torus, and this X is my puncture, and so I've just drawn the unfolded torus, and here's a particular triangulation of the torus. And now you see I can get any other triangulation of the torus by doing SL2Z transformations. So just transforming with integer 2x2 matrix ABCD with determinant 1. And what are the cluster variables? Well, if I go to a different triangulation, then I just see different slopes. So I see lines of rational slopes P over Q, where P over Q is written in lowest terms. So the greatest common divisor of P and Q is 1. Okay? So those are the cluster variables, but there's also a delta associated with exactly the same data. That's because I can also get a delta. So maybe this is a cluster variable, but I get a delta, which is a closed loop on the surface that just doesn't go through the punctures. So that is a closed loop, sort of parallel with slope P over Q. It doesn't go through the punctures. It's just a closed loop on the. It's a closed loop on the torus. So you see here, there's already infinitely many cluster variables and infinitely many deltas. And this is just, remember, the once punctured torus is just these non-planar two-loop vacuum diagrams. Okay, so if I go to where we saw the once punctured torus, we saw it already up here. Okay, so if I look at the once punctured torus, and here I'm drawing this particular diagram. This particular two-loop vacuum diagram I draw on a torus, I draw its dual triangulation, was exactly a once punctured torus. So already this very simple case, non-planar two-loop, we start seeing this phenomenon of an infinite number of cluster variables and an infinite number of deltas even. And the quiver associated with this guy is the dumbest, simplest looking thing. Just this, just 3 sites. This is a 3-dimensional object, 3-dimensional space. And this is the quiver associated with it. It's known as the Markov quiver. And you can easily see if you mutate it, you just get the same quiver over and over again. So again, that's it. There's just one triangulation of the once punctured torus, and all you can do is do SL2Z transformation. But already this is just is fascinating to see what happens to the cluster. These numbers are sort of too small to see, but here I've just represented this tree. Just represents what you get by mutation, starting with this basic cluster and mutating. And what you see is some fractions with slopes of fractions with growing denominators that are actually in one-to-one correspondence with this famous picture of a fairy diagram, if you've seen it. But anyway, it doesn't matter if you've seen it before or not. I can take, so the space naturally divides into 3 branches. And that is, again, kind of like what we saw before. In these 3 branches, the G vectors that you see are determined by linear equations. So just the analog of what we saw before, that the winding variables on the positive winding side, or X winding, is linear in winding. So the action of the mapping class group is linear. Well, here too, it's linear, except in these, it turns out to be linear, except in the, but in these, separately in these 3 chambers. If I take one of these chambers, then this is a sort of picture that I see. Again, the number of variables is growing exponentially. But now this kind of looks like a picture of cosmological evolution, like we're used to in de Sitter space, accelerated expansion, where you sort of double in size. Okay, so now the cluster variables are growing exponentially. But you can do exactly the same things again. Now, I won't draw it at the level of the polytope. I mean, we know what the ABHY realizations of the polytopes are. Let me just back up and draw for you what. But that involves a number of ingredients that I don't have time. I don't want to explain now. But I can just show you what the G vectors look like, just to see if there's some magic. So we're going to do the same thing. The G vectors are 3-dimensional vectors, and I'm going to project them to a 2-dimensional plane, just like we did before. And what you see in the green, so these the sort of purple things up here are the G vectors for the cluster variables. What you see in the green are the cluster cones, and so you see indeed, as usual, there, as we saw before, there are more and more of them. They're starting to fill out the space, but they don't. And unlike before, the sort of novelty here is that now the sort of boundary is this weird sort of fractal-like behavior. And as you add more and more things, it gets more and more. Well, it is a fractal. But there are also deltas. And if I add, so if in this example I go all the way up to keep this. I think I did a smaller one here, but anyway, if I stop somewhere, so now the analog is stopping winding, is I have to stop this time evolution. I have to stop at a certain stage to keep some exponentially large number of variables. I keep all those variables, and I have to keep all the deltas, all the corresponding deltas up to the previous stage. So I would keep all the variables up to here and all the deltas only up to there. And if I do that in this example, then the following lovely thing happens, that here are the deltas, here are all the deltas that you end up keeping. And then you see that the picture fills up nicely if you include, and they're just there, whether you like it or not, there are these cones that involve delta and 2 cluster variables. That's kind of like what we saw before. But you also have cones involving deltas themselves, 2 deltas and 1 cluster variable. And if you take all this collection of cones together, they're non-overlapping, and they tile the space. So that means that the corresponding polytope now has lots of deltas, and it has lots of deltas. It has some ordinary clusters that we associate with Feynman diagrams, as well as these things involving deltas. Okay? So once again, you're always keeping more of the variables. So as we go along, if we wanted to do this thing where we only kept the cluster variables, that's fine. You can always just you can set them all equal to each other, and they will dominate over what you get from the deltas. It's interesting to keep everyone together and to try to interpret what these deltas are. So already here you see that if there's some kind of gravitational interpretation of these deltas, we would somehow have to figure out what it means to have infinitely many deltas. So that's one of the things that we're trying to understand. All right, and just to give a peek to a problem that you might care about more, what happens with 3 punctures at 3 loops and beyond? At 3 loops and beyond, it's basically the same. So essentially, the main difference is whether the growth of the variables is polynomial or exponential. And at 3 loops or beyond, both in this 1 puncture example, but also even for planar diagrams, but at 3 loops and beyond, we have that feature. And even thinking about what the arcs are is more interesting. So for instance, here's a case with 3 loops. So just planar diagrams, 3 loops. I haven't drawn the other punctures here, it doesn't matter. But now you see, what are my arcs? Well, so, you know, I have this arc here. I have this purple arc, but I also have one that winds around in this crazy way before coming and reaching it. And in fact, I told you the mapping class group, in this case, is the braid group. So the braid group on 3 strands is the non-trivial, non-abelian group. And in fact, even labeling the arcs, what the arcs are labeled by, are not labeled by elements of the braid group. That's because a given arc, like this arc breaks the braid group symmetry from B3 to B2, right? Because once I decide that it's talking to puncture 1, I can still do rotations of 2 and 3. So the arcs are actually kind of like you're used to in spontaneous symmetry breaking. The arcs are labeled by cosets of the braid group on 3 strands modulo the braid group on 2 strands. And so there's some nice group theory of the braid group that is going on here. But the result is that in this case, for example, that braid 3 modulo braid 2 is actually just a free group on 2 elements. You can think of those 2 elements as the rotation of 1 and 2 and the rotation of 1 and 3. So if you give any word in A12 and A13, any word in A12 and A13 specifies an arc non-redundantly. Okay? Obviously, if you give me any random word in the braid group, then that also gives you an arc, but it's a very redundant covering. So you want to non-redundantly cover the arc. That's elements of this coset, which are labeled by this free group. So basically give me any word, A12, A13 squared, A12 to the minus 4, etc. But any word like that is associated with what's called the Cayley tree, where in this direction, this would be A12, and then here it would be, then I multiply by A13, then I multiply by A12 inverse, then by A13 again, and so on. Okay? So again, you see this exponential growth. Again, this looks like a cosmological picture, but now it's not a cosmological picture in something that looks like one de Sitter space. It more looks like what we call eternal inflation, where you get a bubble here and it produces its own bubble, and so on. So this is just what the kinematical spaces look like. So this exponential growth means the kinematical spaces are generally cosmological, and so we have to figure out the correct way of thinking about what the dynamics is, and the role of the deltas more generally. But anyway, the strategy is at least so far is the same as what we've been seeing. All right, I think I'm going to stop there. This has been I don't know, over 25 hours of lectures on this topic. So so I'm very, very grateful for the opportunity to kind of talk about all of it. Yes, are there any questions?
Yeah, so Nima, if in the amplitude-hedron, if you went to the non-planar case, you will see some analog of delta, or?
No, I have no idea what. Yeah, I mean that's one hope here is that is to see if we can. I mean, it's so easy to do non-planar things in this story. It would be very nice if there was some way to take inspiration from that back to the amplitude-hedron. I don't see it yet at all. But I think, but we don't really see yet either the relation between the amplitude-hedron and even the isosahedron, right? And this is what we talked about before. There should be a relation between them, not just for vague reasons. You know, even the relation of CHY and the twistor string definitely suggests that we should somehow be able to upgrade these n-3 forms for the isosahedron to 2n-4 forms for the amplitude-hedron. Certainly, there's the relationship at the level of the ordinary string to twistor string worldsheets, and at the level of the way the scattering equations turn into the RSV equation. But that has not yet been understood precisely. So I suspect that we'd have to begin by understanding that. But I agree that it's kind of it's definitely a hint that these geometric. I mean, as I said in the beginning of all of it, you might have thought these geometric ideas are somehow to do with integrability of n equals 4, very special theory, supersymmetry, planarity, blah, blah, blah. Well, okay, now this is completely non-supersymmetric, non-planar. I don't think it has anything to do with that. Of course, I never thought it had anything to do with supersymmetry and integrability, otherwise I wouldn't work on the subject. It's very little about integrability or supersymmetry. But anyway, so we still don't know for a fact that it's not that for n equals 4, but the fact that we see these things in relatively simple places about just to do with triangulations of surfaces and so on makes me think that it is extra encouragement that there should be something not for the n equals 4 story. But yeah, sorry. I mean, you know all of that. I don't know any yet any concrete hint for what it should be. Maybe it's a hint. I mean, again, I don't want to push this analogy of delta with gravity too much because we don't know exactly how to interpret them. It's kind of like gravity. And these small examples, you can really think of the delta pull as factorizing into 2 lower amplitudes the way you would from like a graviton exchange or dilaton exchange. But how to think about them in general? How do we think about the fact of these infinitely many deltas and so on? That I don't yet know. So I don't want to push that analogy too much. But it is. But even roughly speaking, it does say that that to see non-planar things, we should see other things other than the gluons. So in this example, in order to see the more general story, we have to see things beyond just the deltas are telling you there's something extra other than just the scalars in these amplitudes. So maybe we really need to be thinking about we need to be thinking about the analog of that for the amplitude. I don't know. Any other questions or comments? And this is really my last slide or my last comment is just to summarize everything that we've talked about. Over the past few years, we've seen really, I mean, I started the very first lecture with these very grandiose, highfalutin motivations that we somehow have to see the rules of space-time and quantum mechanics coming out of more primitive ingredients. And now we're seeing concrete examples of that. So that's what we've seen in this series of lectures. They're baby examples. They're not fully realistic. They're only about certain kinds of observables, scattering amplitudes, but they're observables where this question can be converted to a relatively sharp one about whether the kind of singularity properties of the amplitudes that reflect locality and unitarity can actually emerge from a different kind of question. And we've seen these emerge from simple new structures directly in kinematical space, where the scattering amplitudes live. We talked about it in the context of all loop planar n equals 4 Yang Mills and the amplituhedron. Now we've talked about it in the context of these non-supersymmetric theories through the 2 loops, some all loop cuts, some double trace contributions, some non-planar vacuum things, and so on. So we're still building up the understanding of what it is, but I think it's heading towards the all loop all orders in one of Ren's story with these Clusterhedra. And I'll say again something I said in the very first lecture. These ideas are directly related to real world physics in some reasonable approximation. Not exactly, but the amplituhedron describes gluon scattering at tree level, and that's what happens dominantly when protons collide. The gluons, the size of protons, collide at high energies. Not just at colliders. Every time a cosmic ray hits the upper atmosphere, this is something which is going on. So these are things that describe natural processes in the actual real world. They've exposed these hidden symmetries and also describe certain universal features of a wide class of theories. As I said, the singularities that are being geometrized by the amplituhedron are all the singularities of a Yang-Mills theory, at least in the planar limit, including the soft singularities. That has nothing to do with supersymmetry. It's just what are the pattern of soft singularities that are allowed in any theory, and it's a very non-trivial fact that that pattern is captured by these positive geometries. It's an extra fact for maximally supersymmetric theories that just being given that information and nothing else forces this D-log form that you can then interpret as the full answer. In more interesting theories, we have singularities in the infrared which are associated with all of these boundaries in the amplitude. And we also have singularities in the ultraviolet, which are something else. And so we have to think about how we can enrich the structure in order to let us see both. But there is a independent fact, independent of building the amplitude by writing this this canonical form. There's just this independent fact that all the singularities are captured by this ab initio geometric object, and that's not a priori obvious that should have been true at all, but it's true, and it's true for anyway, it's true for a wide class of theories. Similarly, for this biadjoint phi cube theory, the singularities we're capturing now are all the really universal ones that don't even care whether you're gluons or gravitons. So they're just the factorizations and nothing else. No soft singularities, but just those at tree level are captured by icosahedra. And well, we're starting to see how we can try to think about them as being captured by geometries more generally. And so there are many questions, open questions, but I'll just end with the one that we've alluded to a couple of times. We don't yet know how these two pictures are related to each other. These two different kinematic spaces, amplituhedra and icosahedra, as we said right at the start, there's a fateful difference, which is that in the amplituhedron we have a kinematic space that labels each individual momentum separately, whereas in the icosahedron we're labeling them in pairs. We're thinking about that's where the two comes from. The fact that we have these surfaces, it's all this two-ness is coming from the fact that that we're talking about Mandelstam invariance. That makes it all the more surprising that the very similar mathematical structures show up, even though we make what looks like a big difference in labeling the kinematic space. But the ideas of cluster algebras, I didn't tell you how cluster algebras are very directly related to total positivity that we saw in the case of the positive Grassmannian. But anyway, there's a very intimate relationship between those set of ideas. And there are more connections besides that are showing up between the amplituhedron and cluster algebras more recently. So it's somewhat mysterious that while the description of the kinematic spaces is so different, that we're seeing similar mathematical structures. And of course, as we said, even more concretely, we know that the picture of the worldsheet, the conventional worldsheet, and the twistor string, or CHY, and the twistor string are closely related. So it would be very funny if there wasn't a direct close relationship between the icosahedron and the amplituhedron, probably to be seen in the version of the momentum amplituhedron rather than the momentum twistor amplituhedron. There's very likely some very close connection there that can be discovered. And again, another big question, but that's something that we're busy trying to think about now, is whether these deltas that we needed to include in the story of the punctured surfaces are whether this picture of the deltas like gravity is more than an analogy. And finally, what do we do with more general theories? And here there's a lot of beautiful work in India, figuring out how to extend ideas at tree level, then one loop quite recently with Stokes polytopes, accordiahedra, and so on. And this is a subject I really want to understand and learn about more. It's very interesting that it's not some totally different thing, that the objects that show up seem to be closely related to the cluster polytopes already. So it'll be, of course, really interesting if these extensions to a clusterhedra also had some analogs in that world. So those are three obvious questions that I will leave you with and stop here. Thanks a lot.
Thank you, Nima. Do you still want to answer a question in the chat?
Yeah, there's a chat. Yeah.
Yes. Okay. Yeah. So there's the first question. I think I answered already about the how we decide what the right hand, whether we take B or C.
That was an old one.
Yeah, that was an old one. So I just see one new one, which is, what is the physical meaning of punctures in the surface? So yeah, so the meaning is sorry. the punctures on the surface are representing loops. Okay, so if we take the simplest example, oh sorry, let me share my screen again. Sorry guys, hold on. Okay, so if I take the simplest example, so let's say I have I'll just draw it as a square. So let me do it. Let's start with 4-point amplitude. Let's start with this box. Then if I draw the dual of this diagram, then I put a point in the middle of all of these squares and then this point in the middle, and I draw this picture. And then, okay. So what you see is that the dual of this box diagram is just the triangulation of a square, but I have this X in the middle, this puncture in the middle, and that puncture exactly represents the loop. The fact that I have represents the fact that I have a loop. So if I'm drawing planar diagrams, if I have L loops, I would have L punctures. Okay, yeah. So you finally asked also about you asked about the G vectors and the laminations, and actually that gives me an opportunity because I explained about computing. I explained about getting the G vectors for all. I explained about getting G vectors for all parts, but not what happens when you have a puncture. So let me actually just finish that story. So let's say let me do this example again. So let's say we have this triangulation now with a puncture. Okay, so 1, 2, 3, 4, and so let's say I have this triangulation. Okay. Okay, and now what I want to do is find the G vector. Let's say for no, I don't. Actually, let me do a slightly different triangulation just for fun. Okay. Okay. So let's say I want to find the G vector for, I want to find the G vector for some arc which is tagged. Let's say I want to find the G vector for this arc, but where it's tagged. Okay. How do I deal with the tagging in general in these pictures where I want to compute the G vector? And the answer is you do exactly what you always, exactly the things that we do before. We draw exactly the same picture. So in this case, I would once again move, to get the lamination, I would move one over a little bit. But when you have a puncture, what you do, and again, this is all, now everything sort of makes a lot of sense when you think that this was really blown up into a little delta. But you sort of keep the puncture there. And if it's tagged, you actually imagine in your lamination that you actually just wind around here infinitely often. Okay, and if it's untagged, it winds around the other way. And so, so if you do that, what happens in your laminations is that, sorry, what happens in your little quadrilaterals is that you might get something that looks like that, and then the windings will look like that. Okay. Well, if that happens, all these windings don't give you anything, and you'd get one. But that is the rule. So the rule for getting the rule for getting the G vectors for given if you start with a given triangulation that doesn't have any tags, that's when it's easiest. If the initial triangulation doesn't have any tags, then you do exactly what we did before. But if you have an arc that ends at a puncture, then in this lamination, instead of ending at the puncture, you just make it wind around one way or the other way, depending on whether it's tagged or untagged, and that gives you the corresponding G vector. So always the picture is tagging and untagging is really secretly coming from winding around a lot one way or winding around a lot the other way. Any other questions?
Nima, I don't want to keep you talking, but any progress on like understanding stringy canonical form or U variables for this infinite case?
None. I mean, I have not thought about it at all. I don't even know whether, I mean, it may even be true that if we made the stringy canonical form where we just throw in all the variables that we keep, including the windings and the deltas, that maybe we just get the right polytope out of that. Even that is, I don't know if that's true or false. But yeah, yeah. I mean, part of the reason that we haven't been pursuing that way of thinking about it is just because, you know, that's a good way of understanding things when you know what it is that you're looking for. But if you just do it like flat out, already the smallest examples have so many variables that there's very little insight into what's going on. Whereas in this APQ case, if you think about it, you know, in the more free-spirited way of equations in kinematic space and so on, you're sort of 80% of the way to the right answer, just writing down the first things that you see in the kinematic spaces. Then you have to think how to glue the edges together. And it said the most non-trivial thing is gluing the positive and the negative guys together. Yeah, but that's the yeah. And also the fact that the other thing is that the fact that the mesh constants have to satisfy relations or they have to live inside their own polytope is also something that seems like it'll be yeah. It won't. Yeah, I'm not sure how that would come out of a simple stringy canonical form picture. It might come out of it by something like, you know, our big polytope not being a simplex or something. But I don't know. I've thought very, very little about it.
More question?
So just more general question for everyone, even Song and Newton, that what's the status of these non-planar terms in CHY? I mean, these multi-trace terms in for bi-adjoint scalars.
Yeah, I don't know.
Sorry, you mean?
Song, do you know?
You mean like some at loop level? What
right?
Like,
yeah.
But they're in the literally. I mean, in the ambi-twistor string language, everything is in linear propagator. So.
Yeah, so that's actually what I was going to say. When you asked this question earlier, Alok, I forgot to mention this point, is that they're not the same because, you know, they're, first of all, the kind of forward limit idea is the idea of adding 2 points. And secondly, you don't see honest, I mean, you don't see normal propagators, linear propagators. You don't see normal propagators. So that's why the one loop CHY is already not the same as the DN polytope.
Right.
Something else that Song has been asking about and emphasizing, and it's correct, is it is interesting to ask how we would get, or if we can get, all the amplitudes from the bi-adjoint theory, rather than just the one where the traces on the 2 colors are the same, right? That's something that, at least geometrically, we don't, at least I don't know how to do, even for DN. So the DN polytope is giving us the one loop amplitude, but only for the sector where the trace on the 2 colors are the same. And if we want the sectors to be different, then at the level of Feynman diagrams, we're just deleting some Feynman diagrams, we're throwing some Feynman diagrams away. But the question is whether what's left still has some kind of polytopal geometric interpretation. And naively, it doesn't look like it. I mean, it's not obvious that it does. In the case of the isosahedron, there were these sort of 2 ways of thinking about that. One of them was that even within one ordering, even for one isosahedron, we could get the other ordering by pushing some of the facets of the isosahedron to infinity. And there was a sort of a natural way of thinking about doing that. So that was one way of doing it. And there was a different way of doing it, a much more satisfying way of doing it, by thinking about this form in the big kinematic space, and then we pull back to different subspaces to get the different orderings. Now in the case of dn, I think there are some obstructions to the first idea, to just imagining taking dn and pushing some faces to infinity.
Right.
And yet, when we don't have any idea for how to think about the sort of big kinematic space at loop level. This question of big kinematic space at loop level is basically, trying to understand is basically the same as understanding what is the good way of labeling loop momenta in general. Of course, we can label them in lots of ways, but what's a canonical way of thinking about what loop momenta are that allows us to talk about the non-planar integrand? We have sidestepped that problem in the discussion that we've had here about the surfaces, precisely by embedding the diagrams in surfaces. The second you embed them in surfaces, you're done. Then there's a canonical notion. Again, on a surface, I can draw the diagrams, the dual diagrams, and everything is fine. But if we don't want to insist on drawing it on the surface, then if we want to have this sort of big kinematical space, if we want to imagine talking about all the orderings at the same time, then we're back to that problem of trying to figure out how to label loop momenta in a way that allows us to talk about the integrand. So these are all old problems. It would be more satisfying if there was some kind of a big kinematic space at loop level and we pull back to different subspaces to get the different orderings. That would really be satisfying. But I think it'll be more satisfying than this picture of pushing walls to infinity. But in any case, the pushing walls to infinity doesn't even seem to work for DN. That's what you concluded, right, Song? I mean, we had a short discussion about this a little while ago. But
yes. I think Chin is also wrong. I mean, we explicitly checked that when you send some facets to infinity, you just lose some vertices.
You lose some things that you want to keep already. Yeah, I mean,
exactly.
You see it already even with the box, right? That's right. Yeah. So, anyway,
speaking of that, I wonder. I mean, shouldn't there be some relation between single chase and double chase amplitude, where you probably won't see it here in your language, right? I mean, for the one loop case.
What kind of relation do you mean? Do you mean
say for gluons, you would write the latter as linear combination of the single chase one.
Yeah, you mean things like KK relations, even, right? Even more basic, right? Yes, absolutely.
Yeah, right.
Absolutely, yeah. I mean, absolutely. That I mean, we would say that already even for tree level, right? At tree level, we have things like KK relations. Never mind BCJ. We have, but even for the bi-adjoint theory, we just have these simple. Well, anyway, in all cases, we have these relations. And if you just see one ordering, you don't see those relations. So if you want to see those relations, well, we have to see various things, big kinematic space, anyway, various connections to the world sheet.
Yeah, it's the same problem.
Yeah, it's the same problem, right? You could hope, I think you can hope that maybe you could hope that if this connection to the surfaces is, I mean, if it works, well, already we could explore it in the cases that work. That, well, already we have a surface, we already have orderings, so maybe the relations are just reordering the points on the boundary, right? So in that case, it would not be so different than the relations that we've seen already before. Yeah.
But wouldn't that be like going towards permutohedra or something like that if you wanted to see this kind of?
Yeah, perhaps. I mean, again, at the tree level, we know that if we just strictly order the points on the boundary, we get isosahedra. If we do more interesting things where we fix two of them and then permute all the rest, we get permutohedra. And all of these things have some natural, well, anyway, they all have some natural interpretation on the world sheet in terms of natural canonical forms on the world sheet. So what I'm saying is that maybe that idea can extend. Like I could take this APQ example, which is double trace, and now maybe there is some interesting geometry if I do the same thing. I fix two of the points on the outside boundary and I sum over the permutations of the inside one. Okay, and maybe that belong with some polytope. I don't know. I mean, I'm just saying that those are. I'm just saying that it doesn't seem so dissimilar anymore. In all cases, we have a disk with a boundary. We have a two-dimensional surface with some boundary, and we're finding relations between permuting the points on the boundary. And that picture is now, yeah. So we have the same. We have the same picture. The ingredients are the same. We can try to look to see whether there's a sort of a geometric reason for those relations. The geometric reason for those relations in the case, but yeah. Yeah, I actually, for that question, I think just thinking about it directly in DN would be interesting, right?
Sorry, you mean like relations between different orderings and so on?
Yeah. How do we think about relations between different orderings in the context of DN? And here, I think we know what the issue is, right? We know that if we think about DN, if we want to have a kind of the closest thing we can have to a worldsheet model for DN, we know that for D4 it's G3, right? And so somehow this notion of different orderings is this notion of different orderings is probably not unconnected to all the different orderings for the 6 in G36, right? But we know there that we get other things, other shapes beyond just the cyclic minor forms. So I don't know what that means. That's the most obvious way to try to find relations, but it would appear that it would give you relations also with other objects that aren't just reorderings of what we have. So it would be, I don't know if the other things that are not just rearrangements of the cyclic minor measure, if they also have simple amplitude interpretation, or maybe we can find relations that don't involve them. I don't know. Do you know off the top of your head what the?
Yeah, I think there are relations just among the Park-Taylors. Yeah.
All right. Well, if there are relations among the Park-Taylors, then yeah, then those should give us relations. And yeah.
Yeah, but that's just for D4. So.
Just even for a D4. Yeah. Well, that would be something already. Perhaps more generally, we could look at in the U space picture. We know that there are going to be different shapes in this extended real U space, but maybe there's a reason why there are relations only between all the shapes that look the same for general N.
Also for CN, there are definitely such relations just among the cyclohedron. So
I see. All right. Cool.
That's encouraging. Yeah.
Right. That's very encouraging. That is very encouraging indeed. But I mean, sort of even more interesting would be well, I don't know. Perhaps the other relations can be used to compute the other guys. I don't know if that would be really cool if we could sort of compute the other funny guys, so that that's actually really unobvious whether, well, okay, here's a well-posed question, right? We have the number n-3 factorial at tree level, and we also know that number is the Euler characteristic of the space, or the dimension of the middle dimensional twisted cohomology. Well, we could compute that number for Dn. Well, even for Dn, if you remember, there were these complicated polynomials. But anyway, for any n, you could compute it, and then you get some number for the number of independent integrals. And there's just a question: is that number actually equal to the total number of things we understand, or not? Do you know if that's true or false already for small for Cn? In other words,
sorry, you're talking about BCJ basis, not KK, right?
Yeah, I'm talking about BCJ. I'm talking about well, we could also talk about it for KK for that matter. Yeah, let's actually talk about it for KK. I prefer to talk about it for KK first. Yeah. So if we do KK, then is it true that there's that the size of the basis that you get from the point counts for the cohomology, is it true the size of the basis is smaller than the number of independent, dn spaces that we think we should have. In other words, is it possible that there's a basis for the ordinary cohomology just given in terms of the pieces we understand, or the pieces we like?
So I thought why it should be smaller, not equal?
Oh, maybe equal, smaller than or equal to, but it doesn't have to be. But sorry,
Yeah.
in general, smaller than, right? Even for tree level, the number of orderings is n minus 1 factorial over 2, which is bigger than the size of the basis. In other words, there are even relations, but no, it should be smaller than, right?
You're not talking about independent ones. You're just listing all the orderings, right?
Yeah, I'm just listing all the orderings. Yeah, so let's
But that's a different counting. You plug in p equals -1, you get that counting.
Yeah, that's right. Yeah, so but no, because that p equals -1 is sort of all orderings, including ones that we don't understand.
Oh, you mean the normal guys?
I just mean the normal ones, exactly. If we take the normal ones that just come from reordering guys,
for type B and C, for type B and C, we know for sure it's smaller. Yeah, strictly smaller than a number of normal guys. For type D, I don't know.
Then that's very encouraging. That is very encouraging. So if that's also true for type D, then maybe in fact, maybe everything is given by orderings, and then that would be very cool. Then I think we might conceptually understand all these relations, at least up to one loop, in the same way that we do at the tree level. If it's true.
Right. Okay. Any more questions?
So sorry, this is very, very speculative. But since G36 is, this GR36 is same as D4, do you think there's any relation for the, if you took this generalized bi-adjoint scalar 6 particle through some forward scattering, would have some relation with one loop?
Oh, the relation is much more, the relation is much more direct than that. If you take that generalized, if you take those generalized amplitudes associated with G36,
yes, they
are the canonical form of the corresponding polytope, and that is almost the D4 polytope. Okay, but they're almost the D4 polytope. So now there's an amusing little difference that the D4 the D4 polytope has, I forget how many, well, it has 16 faces. I forget the things in the middle, but it has like 100 edges and 50 vertices. Whereas the thing that you get from this guy has 48 and 96. Okay. Sorry, 48 and 98. I guess.
98.
Yeah, 48 and 98. Sorry. So that polytope is like the D4 polytope, where you take two of the edges and you shrink them to a point. Okay, so it's almost the same, but it does make a bit of a difference. Now this polytope is no longer simple. It's not a simple polytope, so anyway, so you don't have this quote unquote Feynman diagram triangulation and so on, but they're very simply related to each other. And in fact, if you wanted to literally get the D4 polytope, this is the story of these cluster stringy canonical forms. What you would do in this G36 language is not only put in these sort of Cohen-Nielsen-like factors. Oh, sorry, I'm not. Well, anyway, if you said in the stringy canonical form language, you put in powers not just of minors, but also two other variables that are cluster variables of G36, but are not minors. And if you put those two in, then you sort of further blow up that generalized bi-adjoint scalar polytope into the honest one-loop polytope. But yeah, you're right. They're almost the same. In this example, the difference is pretty small, just losing these two edges, but they're almost otherwise the same.
Sorry, does the polytope picture extend to all K these generalized bi-adjoint amplitudes?
Oh, I don't know. I know nothing about it. I don't know what loops are supposed to mean on those theories yet. So
okay.
so
no, even at tree level.
even at tree level. Well, yes. There is a polytope, and again, one way of thinking about it is that what those theories are associated with generalizations of the string integral, where instead of having Kobe-Nielsen factors, which are 2 by 2 minors to powers, you put all the k by k minors to powers. Okay, now now you run the story of stringy canonical forms, and that gives you a certain polytope. Okay, there's a concrete polytope, and these amplitudes are the canonical forms of those polytopes. So there are some polytopes there. And the stringy canonical form tells you how to construct them even. There are some, but they're not like these. They're not exactly. They're sort of cousins of these dissociahedra, but in general they're not simple polytopes. Also, their factorization properties are not exactly like they're not factorizing into 2. They have some facets on which you factorize into 3 and higher pieces. So I think but all of them are associated with polytopes. That's sort of guaranteed. That's a sort of simple guarantee that from the connection to stringy canonical forms is that that there are polytopes associated with all of them.
So one of the features of the generalized biodirected amplitudes is that they have very different pole structures. I mean, higher order poles, even when you do soft factorization. Now, is it something that can be seen from these polytope picture?
Very much so. Very much so. Yeah, that there's a kind of understanding for what the facet structure of those polytopes looks like. And I mean, that's a separate story. I haven't talked about it, but that facet structure, when you apply it for the case of the icosahedron, you see, so in great generality for any GKN, there's these amplitudes are the canonical forms for certain polytopes. And I can describe the facets of these polytopes of all dimensionalities as associated with what are known as certain kinds of triangulations of the hypersimplex. Or anyway, this is a longer story, but without telling you any of the details, what you can see just geometrically, very simply, is that for the case of the icosahedron, every facet just looks like factorizing into 2 lower icosahedra. Okay, so that's for these generalized things, that's not true. There's some facets that look like they factor into 2. There are other facets that factor into 3 and higher things, and the pattern of factorization is reflected in the kind of subdivisions of the hypersimplex that you're allowed to have. So there's something deeply geometric about it. Whether it's sort of I mean, I haven't worked on this. I've not worked on the subject I mean, I've followed it. I've not worked on it in detail. So, I mean, one would have to actually work out what it looks like if you want to know exactly what the facet structure is, exactly what the pole structure is. But it's completely clear ahead of time that it's not like the normal amplitudes, and it has these interesting features of factorizing into 2, 3 higher pieces, and so on. So they're extremely interesting objects. But it's a kind of it's a different direction. What's fascinating is that those kind of polytopes might be relevant to the question of n equals 4 amplitudes, not at the level of the integrand, but at the level of the final answer. And there is some relation between the cluster structure that you see in symbol entries for n equals 4 super Yang-Mills, and exactly these sort of these polytopes that you associate with these Grassmannian string integrals, which are the same things that give you these generalized scalar amplitudes. So there's some very beautiful geometry that's associated with them, and for the particular case of G4n, they might even be related to n equals 4 amplitudes in a very interesting way. But what I don't know is if there's in any of those stories, you see, if you start with, depending on where you start, if you start, let's say, from these stringy canonical forms, then all these things are sort of simply connected to each other. It's just a question of whether you're doing G2n, G3n, GKN, or maybe you're integrating over these U spaces for cluster algebras. So that's a way of generating all kinds interesting polytopes that guaranteed to have interesting factorization properties and so on and so forth. And they're all sort of related in that way. On the other hand, for the Clusterhedra and these and the generalizations, we have the sort of separate picture, this ab initio picture of the kinematic space and the wave equation, these sort of dynamical questions that give you the same polytope. I don't know if there's an analog of that sort of ab initio starting point for these other examples. There might be. I think if they exist, they would have to involve some new ideas because, at least in the language of stringy integrals, the existence, the fact that there's this ABHY like ab initio presentation of them is related to the fact that starting from these stringy canonical forms, you naturally discover these U variables. And I think in these more general examples, we don't have an understanding of a canonical set of U variables. Well, they satisfy relations between each other, and it's anyway the same extremely simple thing that happens for generalized Clusterhedra does not happen for them. So that makes me think that similarly some wrinkle, some new ingredient has got to be added to give an ab initio explanation of an ABHY like realization for them. So from that point of view, they're a little bit further apart. From the point of view of stringy canonical forms, they're on top of each other. They're just, you very simply go from one to the other. And all these things are rather closely related to each other.
Okay, thank you.
Any other questions, guys? All right, I don't hear any calls for more questions. So I'm presuming that even these 18 people that seem to be here are mostly asleep. I mean, I would hope they are. But anyway,
Maybe we can all
okay.
unmute and thank.
Yeah, maybe
Yeah.
we should all give Nima a big
Big.
Yeah.
All right.
Yeah. Thanks, Nima.
Thanks.
Thank you, Nima. Yeah.
I had a lot of fun. Thank you very much, guys. You know, when I was doing a sabbatical at Harvard last semester, and the entire semester I gave lectures, you know, normal lectures, and I think the total number of hours of lectures I gave in these past 6 days is larger than the number of lectures that I gave in the entire semester.
Oh, really? Wow.
Thank you. Thank you for giving me the opportunity to do that. All right. Okay. Thanks a lot, guys.
Thanks.
Okay, thank you.
Bye. Bye.
Okay.
See you.
Bye-bye.
Okay.
Bye.